It's 9 o'clock by my watch, so we'll go ahead and get things started. If you're still in the South Ballroom having breakfast, you're welcome to come and join us here in the North Ballroom. You'll have a much better view of the screens. All right, we'll go ahead and get started. My name is Brady Hardiman. I'm an associate professor in forestry and natural resources and in the School of Sustainability Engineering and Environmental Engineering here at Purdue. It's my distinct pleasure to welcome you all to Purdue University and to the first International Conference on Applications and Solutions in Digital Forestry. Before we get started, I have some announcements and some logistical things to note. First, we are in the Purdue Memorial Union. These two rooms, the North Ballroom that we're in now and the South Ballroom, will be our home base over the next couple of days. We have sponsors and exhibitors set up in the South Ballroom, and our meals and coffee and snacks during breaks will also be in the South Ballroom. Restrooms are to my right, out these doors. We also have restrooms out the south end of the South Ballroom. If you can't find one, just ask somebody that has a shirt that says Digital Forestry on it, and we'll happy to direct you there. Weather for the next couple days is supposed to be great, so in the very unlikely event of a tornado, we are to exit south through the South Ballroom and down the stairs to the basement. In case of fire or any other reason we need to evacuate, we will leave out this door to the right, into the hallway to the right, and outside into the courtyard behind me. If you are intending to get continuing forestry education credits for this conference, make sure you've checked in at the registration desk and let them know that you're interested, and they'll get you set up for that. The conference program, which you should have all received when you registered or when you checked in at the registration table, lays out what's happening and when and where, but I'll also be playing director a little bit as we go to help keep us all oriented and on schedule. If you have questions or need assistance, you'll want to look for the conference planning team. Can those folks raise their hand? Jackie Getson, Amy Winger, Amy Blake, and Nancy Kramer, who are, it looks like, probably all back at the registration table. Yes, there they are, way back in the back. But if you need any help, the registration table will be able to help you with anything. Okay, so now that our announcements are done, we'll go ahead and get started. I'm very happy to welcome you all. As I said, we're pleased to have such a large group. We have researchers, practitioners, industry leaders, and partners here together to explore emerging technologies and their applications across digital forestry. We're really excited. We think this is the first conference of its kind to bring together so many people from across the forestry industry and all of various applications. This conference has been organized by Purdue's Institute for Digital Forestry. And so we're going to start out with a few words from our director, Dr. Song-Lin Fei, professor in forestry and natural resources, Dean's Chair of Remote Sensing in the College of Agriculture, and the founding director of the Institute for Digital Forestry. Song-Lin?
Well, good morning. Welcome to Purdue, and welcome to this Application and Solutions for Digital Forestry International Conference. This is a very, very exciting moment, and it is absolute my privilege to welcome you to see the beautiful Purdue Memorial Union filled with these great minds of wonderful participants here. As Brady just briefly mentioned, we really have these world-renowned speakers here. We have the forward-thinking industry leaders here, and we have the dedicated public agencies representatives here. And also importantly, we have our talented students, the future innovators in this room. And I think you all earn your very common title here, which I think you guys are pioneers of digital forestry. And I wanted to extend a very special welcome to the incredible lineup that we have for our speakers. They are traveling really across the globe, right? We have presenters from Europe, we have presenters from Asia, We have presenters all across North America, and then we have participants from other regions of the globe. And so this is really highlighting something quite important, because the challenge of the forestry that we have isn't a global challenge, which requires a global collaboration and solutions. I also like to thank our sponsors, and please visit them. They are in the back of the South Wall room. It's their generosity that makes this conference possible, so spend some time with them. And all right, so for this conference that we were having here, right, for the next 2 days or so, we are here not just meeting here, share a few abstract concepts or share some theoretical debates here, but what we are here for is, as what we, in our title of the conference here, we are trying to make tools and solutions that to address the real world problems. So I hope that in the next few days that you ask some good questions, right? How can we scale these tools from the individual plots to the national scale? How do we ensure that we're building tools that with our stakeholders, not just for them? Think about how they be part of this digital solutions. And forestry has been changing in a rapid way. You think about when we start digital forestry, we're always thinking about, well, forestry isn't a very, very nice field. I enjoyed because the outdoor opportunities and sceneries that draws me into this. And we often forestry being viewed as a forestry sort of a measurement, but it's also a field of patience, right? I always joking, like each of us are tree huggers. We like to, when we measure DBH, we hug a tree at a time. And so it is in a field of slow but patient field. But we have been dragging our feet, measuring every plot. We have been enjoying the field. But meanwhile, we have the digital technology sort of running towards us at a scale that is unprecedented. And how can we take advantage of this? So there are multiple of these key themes are now emerging up, right? They are, in my view, they are, at least through the program that we're going to be experiencing in the next 2 days, there are 3 things are coming up very apparently. We have much advanced sensing technologies. These are from, what I call from iPhone to the cell phone to satellite. We can now have the satellite sensors that at 1-foot resolution on the Earth, or we can have as a powerful cell phone in your pocket that can have lidars and have other tools out there. The second theme out there is that very apparent to us is that AI and intelligence, cloud computing, all that is also at our fingertip. And you like it or not, it is here. And it is here to stay. And you can make things much faster. One my collaborators sit in the back from mechanical engineering, we were saying, right, now you can make an app on your phone with help an AI in an hour, right? Yesterday we demonstrated some of the tools that a complicated platform that can be done within a week. So it is here to stay. And how can we take advantage of these digital technologies to advance forestry? And the third thing I think is, it's a word that has been maybe a little bit abused and overused, but it's a digital twin and the environmental intelligence. We have things in a level, and which is going to be highlighted by our keynote speaker, Dr. Juha Hyyppa, in a moment, that we are talking about individual tree intelligence. So how can we put these all together? So I challenge us for the next couple of days that we, thinking about this in a more a way of how to make the technology connected to solutions. If you are one of the researchers or developers, talk to the end users, thinking about, hey, how can I make my tools and solutions more useful? And if you are the government agency folks or municipal or practitioners or managers, thinking about challenge the presenters, the researchers, and say, hey, how can we work together to make this solution better at scale? So I really hope that you can enjoy this conference and bring some ideas back home and make this the digital solutions at scale. With that, I'd like to introduce our next speaker. Well, we have Professor Dan De Laurentiis, who is our, first of all, I'll introduce him as a professor, okay? He's the Bruce Rees Professor at Aeronautics and I never can say that right.
Aeronautics and Astronautics.
Department, but he's also our Executive Vice President for Research. So Dan, welcome.
Thank you very much. So one correction, which will be good news. I'm not a speaker. I'm just someone here to do two things: welcome you, and also brag a little bit about Purdue. I will try to, it is part of my job description, I will try to do more of the first, and for the second, I will have to do some of that, but really it's going to be bragging about our people, because that's, for those of you that are newcomers to Purdue, and certainly at this inaugural event, I hope what you see, and I highly suspect you'll see that what makes this a magical place and an amazing initiative are the people. So I'm going to start actually there by positively embarrassing our director, Songlin Fei, who just at this stage about a month ago received Purdue's highest and most prestigious award for innovation in the natural sciences, the Herbert Newby McCoy Award. So let's give him another round of applause for that. And actually, prior to that, sort of the award ceremony was in the afternoon. In the morning, we had him give a lecture along with two other prestigious award winners in more of the engineering and applied sciences, as well as in our social and liberal arts area. And so that's where I learned most about the initiatives and his own research. And I also know he mentioned the amount of patience it takes to work in this field. I'm not cut out for that. I work on supersonic and hypersonic aircraft, so that's kind of my speed. But what I learned is even in the world of digital and the innovative things that all of you are doing in this, digital transformation, that's just so central. So. Just a few highlights on that. Certainly we are very proud at Purdue to lead the way in new ideas and initiatives, and certainly in the broader campus environment. Digitalization, digital transformation, and what we call physical AI are really a highlight and a centerpiece of what we do. I think a great partner to the Institute for Digital Forestry is our Institute for Physical AI, which has a lot of overlapping faculty that was established about 2.5 or 3 years ago through a generous gift from the Lilly Endowment here in Indiana. And just a whole number of other areas and initiatives across the spectrum. We have amazing things going on using digital twinning technologies in our materials discovery area, our semiconductor area, and again, and I have to admit, I'm a very interdisciplinary person myself in my own scholarly activity and research, but also in my passion areas. And prior to this role, I led our institutes and centers in Discovery Park, and our current leader of that group is here, Raise your hand somewhere. There he is in the back. That's sort of another part of our ecosystem. So really, the digital transformation and the opportunities therein are just permeating throughout the campus. Again, apologies, but I have to do this. The substrate for all of that is helped significantly by things like a top 3 College of Agriculture, a top 5 College of Engineering, other top-ranked programs and everything. So it really is a great community of scholars here who are very passionate and sometimes impatient. Part of the job I have is having impatient faculty come to me, but I don't mind that because in all cases, in my experience so far, those faculty are impatient because they want to change the world faster than they're encumbered by some constraints either within Purdue or outside the campus, and my job and my team is to move those obstacles out of their way. So turning back to all of you, again, thank you for being here. I'm told we'll have more than 200 registrants. I can almost count each of you all are like little trees, right? And I can use some algorithms to count you, but I'm going to say 200 are already here. And 26 states, I've been told, and 6 countries, perhaps more. So welcome. I myself, on Sunday, am flying to Japan with a larger Purdue team to advance some of our partnerships there in both the university and industry ecosystems. So again, especially for those of you that are new to Purdue at this inaugural event, I want you to know that you are welcome. The leadership here at Purdue, many of which you'll meet today, but I'm speaking also on behalf of our current president, Mung Chang, and our soon-to-be president, again, Mitch Daniels. So we have a president transition going on here. But this institute and the people in it are exactly what all of our leaders at Purdue have been trying to foster on the campus. And so for all of you that are new here, please partner with us and don't be shy about telling people like me when there's something standing in the way of partnering with Purdue. So again, welcome and thank you. Ooh. So I forgot one last part of my job is to institute the co-director of the Institute for Digital Forestry and my very good friend, Ayman Habib. Here he comes.
Good morning, everyone. So my job today is to introduce our distinguished keynote speaker. So I'm really, really delighted to and have the great pleasure to introduce Professor Juha Hyyppa. Hopefully I said this right. So Juha is from the Finnish Geospatial Research Institute, FGI. He's really one of the leading pioneers in laser scanning and geospatial technologies for forest inventory. Juha is not only working with forests, but yesterday I understood almost 70% of his work is related to forests. So for decades, Juha has been at the forefront of advancing how trees are measured, mapped, and understood. And through his leadership of the internationally renowned Center of Excellence in Laser Scanning Research, or COE-LASR, he has helped establish airborne, terrestrial, mobile, and multispectral laser scanning as a foundational technology for modern forest inventory and environmental monitoring. His work has fundamentally transformed the field from stand-level estimation to detailed individual tree assessment, enabling more accurate measurements of forest structure, biomass, biodiversity, and carbon dynamics. Quite recently, through Finland's Unite flagship on forest-human-machine interplay, Professor Hyyppa has contributed to integrating laser scanning, AI, and digital technologies to support the future of precision forestry and sustainable forest management. Today, as Songlim mentioned, Professor Hyyppa will share with us insights into the future of laser scanning for forest inventory, intelligent trees, and this will be reshaping how forests are monitoring, managed around the world. So please join me in giving a very warm welcome to Professor Hyyppa.
Thank you, Ayman and Songli, for inviting me. Good morning, ladies and gentlemen. My topic deals with, perhaps I put the next slide. Okay, so deals with individual tree-level inventories and using disruptive technique to measuring. I'm coming from Finnish Geospatial Research Institute, which formerly was a Finnish Geodetic Institute, so anyhow, FGI. So this is the content of my presentation is first, what is FGI actually? What is the Finnish environment for smart forestry? Then I have 4 cases I need to select. And I started from digital twins, and I talk about certain biodiversity. And then some concluding comments. So what is FGI? Don't say this Scholar GPS is bullshit. I really like this. So FGI is a research institute in Finland, and I'm leading the department for remote sensing and photogrammetry, and we have really little budget funding, so 90% of is paid by outside projects. If you look at this ranking, so Scholar GPS gives the ranking, global ranking, and if you look at the specialties, so we are small, so we only work with specialties, so there are a couple of keywords like unmanned aerial vehicle, photogrammetry and laser scanning, and it says we are ranked 1 in the world. That is for lifetime, so for 5 years, last 5 years, no, because there are more money somewhere else. And basically when I came there for 27 years ago, they didn't know much about this drone stuff, and they didn't know anything about laser scanning, so I started this, and photogrammetry is basically Eija Honkavaara has led it that. When I started, I said to Eija, you lead that, and we jointly did the department. Okay, some about this smart forestry, so Finland has been actually pioneering in this global bioeconomy infrastructure, or developing it. And to get some understanding about how we feel about forest is that in Europe, so that we have 10% of European forest cover. We have this forest industry employs 140,000 people in Finland. We have 5.5 million people in total. We are one of the largest producers in Europe for paperboard, graphic paper, and sawn timber, and everything is exported. So with all products, 60 or 90% is exported globally, and that means 17% of Finnish export. Okay, some 20 years ago, perhaps it was 30%. We have a national plan that this bioeconomy, that includes also other than forest bioeconomy, it will be then 100 billion bioeconomy target. And we still have quite a large number of protected forest. Of course, it could be bigger. They are forest owners, so basically more than 700,000 people get revenues from forest in Finland, which is 14% of the population. We have been pioneering cut-to-length harvesting methods, and I would say that we have also pioneered in these individual tree-based digital twins. Related to biodiversity, why I raised that, everybody's talking about global change, but forest operations are actually putting endangerment of a lot of species. So it's 25 times bigger amount of species are in danger compared to global change. So we somehow need to preserve them. In Finland, it basically means that if we can detect aspen and down dead wood or standing dead wood beforehand and leave them out of forest operation, it could save a lot of species. Then some facts about our relation with forest is that 96% of adult population is some kind of forest outdoor activity every year. 60% pick berries for their own use or sell. And then we have so-called every man's forest, so we can go to any forest and pick berries, mushrooms. You need to have a permission to hunt, but so basically that is perhaps one of the reasons why Finland has been recorded as like a most happy nation in the whole world. So for, I don't know, 5 or 7 times in consecutive. Okay, we have this flagship. So the flagship means that you should have a brilliant research, but you should have also industrial and society impact. This is the starting ecosystem when we started in 2020. So we have one of the, or many of the European leading forest companies backing us. So we have Ponsse and we have these 3 major forest companies in Finland, which are among the top 6 in Europe. Okay, then I came to a topic. So the first topic is individual tree detection and digital twin. So my background in that is that most probably I was the first who ever published that use ALS for individual tree detection. That was 99. We also had I wanted to make sure that it's unique, so that we also had a US patent on that, so, but okay, it's old. If you talk about individual tree detection, so basically today we want to process the point cloud. Previously it was about using raster data. But those who don't know much about that, so you have a point cloud, you calculate the DTM, which is the lowest hit. You get the DSM, which is the top of the, and the difference is actually canopy height. And you can use this canopy height just to model the trees, and it's actually very accurate. Then you get some near-surface vegetation. You can even make like bilberry maps out of that. You get tree stems. So the higher is the point density, the more you get this tree stem information. At the other extent is that you model the tree stems out of that data, but then you need more than 1,000 points per square meter. This is an old comparison what we did 12 years ago, and we compared space-bound data, so there is worldview 2, then there is aerial images, AI, and then there are ALS techniques, so that we try to find how much you get the trees detected using these techniques. And you see that diameter breast height is there on the bottom. And basically, if you talk about trees with a diameter less than 10 centimeters, so that basically you can get like maximum of 20% of them with ALS, but ALS is still the best. And basically, if you look at that satellite data, perhaps provides you less than 50% of the trees. And still, that is basically used everywhere. In Finland, we have a national laser scanning program. Actually, that is thanks to our research. So, started in 2008, we first had like 1 pulse per square meter, and starting 2020, we have 5 pulses per square meter, and now it's 20 pulses. And Sweden copied the first system to Sweden, and Estonian first ALS test flight was actually done by my department more than 20 years ago. Okay, when we get this 5-point data, so I wanted to show that you can do this individual tree stuff. And we have already, actually, it was just a MATLAB code, but we parallelize it and run it on a desktop. And basically, 1% of the Finnish whole territory was one production block, and we process it in 4 days. And we get 100 million trees. And that was basically what we have promised to do. We published it, so if you want to get the details, you can find it here. But we didn't stop for the first, even though our project only promised to analyze the first, only one production block. We continued. Today we have actually covered the whole of Finland at individual tree level. But we have this public demonstration, or almost public, so there are 150 users. So these green areas in Finland we have processed at individual tree level using this same algorithm. And so there are 6 billion trees there. And basically what we found is 92% of log-sized trees. If you look at the distribution, here is how we get this 90. So if we talk about log-sized trees, it's trees bigger than 20 centimeters in diameter, so that is 92% what we found. If you go to this level where it's close to 0, so something like 5 centimeters, so we get really few with this 5-point data. Related to species accuracy is that if you look at the diagonal, but we have only 3 species in Finland what we record, so it's spruce, pine and deciduous. Deciduous covers everything else. In future it should be also aspen and deadwood. It's more than 80%, and that is if you have training data from the same area. If you don't have any training data and you are using training data from like 200 kilometers away, then it drops depending on the characteristics. And the reason is that the intensity is not stable in that way because there are different systems and different areas and even the absolute level, even though we try to calibrate. Then if you look at the other, there is this 2%, so that's actually the height accuracy, it's 2%. So we are talking about half a meter accuracy, or sometimes 1 meter. If we talk about diameter breast height, even with this national data, it's 15%. And this 15% means actually that it's 30% for the volume and biomass. And this individual tree technique is actually, it's quite robust. So we have studied that if you train data in one area, then you go 400 kilometers away. So the x-axis is the distance between training and testing. So then you find out actually that the volume accuracy drops from, or the error goes from 30 to 34, but it's not a big increase. So individual tree techniques, at least in Finland, it seems to be robust. Of course, there are some, transfer is not that easy when you go to Lapland, which is slightly different territory. The same technique has been also used for creating a virtual forest. And this is just an image which tells this is the forest, and this is the automatically created virtual forest. So we can create this kind of virtual forest from the whole of Finland using the same data. And if you go back and forth, you see that, okay, there are errors, there are some trees of the wrong species, but that it goes to this 80% rule. And there are some trees in wrong places, but it's because this is 5-point data. This transferability has also been studied more detailed in another paper, and you are pleased to go there. I'm sending actually most of my slides to you if you like. And here is the strategy what we thought to do is that so that if you are, for example, studying this Lahti region, so you can use the nearest area, or whether you are using all the southern Finland data, and we are studying this kind of scenarios. The reason why we do this is that instead of measuring 3 million individual trees by the forestry center, so we provide them some options that perhaps there are other options, so of course they have people to do it. Change detection, that's what we have studied a lot. We also had a US patent, so this is an old image, it's more than 25 years, so it was between 98 and 2001, somebody built a power line, and then you could see that there are individual trees removed and a couple of branches. This is now going into practice in that way that we have this 5-point data and 20-point data. We can calibrate what is the bias between this increase of point density, and after that we can calculate with a few decimeter accuracy most of the dominant and codominant. For lower level trees it's not possible because 5-point data is not enough to detect the suppressed trees. So status today, what is now happening? Our forestry center has said that they make this individual tree technique now operational. So this 20-point is planned for that. So the first national laser scanning was due to the elevation model, second was due to the forestry, and now the third one is to making this individual tree technique available. And our implementation we have, if you go to this metsäkanta.com, so that is the, of course you need a passport, but if you read the text you get an impression how it is. It is actually the world's biggest database for forestry. And it was just done in one project to demonstrate this is possible. Then I go to the second topic, which is the automation of field reference collection. So that's me. I don't know, it's 35 or 40 years ago. So there are many topics, but the main problem is that you don't have a single processing flow to make the field reference automatically. And how much reference is needed. But at least in Finland, half of the resources are put on collecting reference data and half goes to this airborne laser scanning. So the interpretation it's something like 20 cents per hectare. So there are many techniques, so most of you most probably use TLS, and that's very nice. That's the highest quality data what you get, but it's not always effective, so cost effective. So if you have mobile laser scanning, it's 4 or 5 times or 10 times faster. And there are many techniques to use for, you can have backpack or handheld or under canopy drone or even above canopy drone data, or in future you may have harvester mobile laser scanning to do it. And that was a state of art some 2019 when Xinglian Lian from our group, he wanted to test what is the accuracy of mobile LiDAR compared to TLS and UAV. And in UAV you use the individual concept where you estimate the diameters of trees. And basically the outcome was pretty bad. So mobile LiDAR was the worst of basically of all these. But what he did is that he used the georeference point cloud and as it is. And okay, that was the topic why we continued the research and said that perhaps we have a better way to do it. So first of all, Xinglian reconstructed the trunks. We said that, okay, we don't need to reconstruct, we are using stem curves. In Finland, the trees are straight. So we started to use stem curves, and the lowest log is the lowest value. We get a lot of data. We don't want to process the diameter breast height because you get the whole stem curve. Why don't you use it? So we started to use stem curve, and we get the tree height, and we had a model. And you can put your own model if you like there. And if you want to get the diameter breast height, then we estimate it from the stem curve, because sometimes the diameter breast height is shadowed by other trees. So that was the first logic. Second logic was that on the upper side you see that most of this kind of techniques are based on robotic slam. And in robotic slam there is a drift. They try to cover this with these loop closures. But they are not enough, these loop closures anyhow, so that you get the trees like there are displacement, and depending on the case, it's always look like that. So what we did, we split the data into time intervals, so like 1 second intervals, and then merge them together. It's like a post-slam algorithm. But we could do it, we didn't need to do it in real time or near real time. But then we get the lower image. And it improved, of course, the results. The third thing what we started to do is that because segmentation doesn't provide you the final results, we divided the segment data with clustering and find if there are 2 or 3 trees in the same segment. And there are enough points in this mobile laser scanning and TLS for that. And the fourth thing, when we work with backpack, in backpack we are also always using 2D data. Of course it's 3D data, or this kind of multi-beam scanners are nice. But sometimes we use this 2D data because the range resolution of 2D systems is still better, and there are certain added value in that, and we can even create this multispectral data from the forest. And then we started to use this high quality arcs. So when there are branches, we don't use this. And it improved the stem curve estimation. Of course, it reduces the amount of stem curves what we get, but anyhow, if somebody is interested in diameter breast height, so we can also drop some other areas. Okay, then we started to do testing. We did like this under canopy drone, and of course we didn't have an under canopy drone, but it was manually assisted in certain way, but we get the same data what you can get today with this under canopy drone, and we could test it, the accuracy already in 2019, 2020. Then we compared it with other techniques, handheld, above canopy, and get the first results. On the left side you see an easy forest plots, outcome of easy plots. On the right side you see from difficult plots. And the first bars are based on mobile LiDAR, and then the next 3 bars are coming from above canopy UAV, and then the field measurement is the last one. So basically what you see is this mobile LiDAR is better than even field measurements. That was really contradiction of what Xinglian showed it, but that was because we do these steps in the processing and it improved. So that was the first time actually I understood that anybody get accuracy what is adequate for operational work. So when you get like a volume at 10%, that is the same accuracy what you get by manual field measurements. So then we continued the benchmarking, and in that second benchmarking we corrected the beam size, because when the laser beam hits the tree trunk, it's enough that only one corner of the beam hits it, and then you assume that the tree diameter is much bigger. and we correct it. And you can simply correct it by this kind of distance correction. It's a linear model is enough. And if this is the result, so above is the diameter and stem curve, and this is uncorrected data, and in this test we have hover map, we have deep forestry system, we have handheld systems, and also some others. And basically they reduced more than 50%. It was from 50 to 90% what the results improved. So basically root mean squared errors goes down, and the bias really goes down. Then we continued the benchmark because we wanted to know what is the accuracy. If you have a SLAM-based system, mobile laser scanning system in the forest, so how accurately you get the tree positions or whatever you get. And we constructed a test line where the reference was, so the tree positions were measured with geodetic techniques. And also we had very high density laser data. With high density, I mean now 1,000 points per square meter, and then we estimate what is the trunk, like the lowest lock, and took the center. And then we get this kind of results. So the helials in the above is that you have the geodetic reference, helials is our very dense data, and then we get 6 centimeters. So basically it's even possible to use airborne laser scanning to create geodetic network into the forest using this kind of very dense. Most probably any drone can do it, but you need to test it because of this beam divergence issue. And when we use that, we also notice that all these SLAM-based, so ZEP horizon deep forestry and hover map, they provided an accuracy of between 10 and 15 centimeters, which is nice. That is actually adequate for creating the field reference. What then? Then we thought that this still requires you need to do the field work, you need to go to the field. Why don't you do it above the canopy? And we already had an idea, and we published it 2017 that you have a drone, but in that time we used Velodyne, and Velodyne has a big beam, and we didn't have the tools to correct it. So we concluded that it's more accurate to estimate it than measure it directly. But in 22, then we put Regal Vux on a helicopter. So it's basically the same as a helicopter, but we wanted to tilt it 15 degrees to get more hits from the tree trunks. And then basically what we found out that we didn't find not all the trees. So here is the data looks like that. So you see that there is trunks are visible, but this is very dense, like 1,000 points per square meter. And we found that we have 3 different test sites, and we found that like 60% of trees were found with a technique. And when we started to compare the results with some other results where they have flown UAV basically inside the canopy in the very sparse areas, we saw that our results, which were between 2 to 3 centimeters for diameter, they were better because nobody else has never get there. So they ranges from like 4 to 8 centimeters before that. Okay, the key message, I'm not going into details, but basically the key message today is that our forestry center is now interested in this kind of automation technology. And they want, this summer we are doing 150 very large plots. And at the time they are also doing manual measurements, and there is a competition. So we are using our data for training the ALS. They are using there to train the ALS. And then there are certain test areas. We will see which one gives the better results. We already know in advance that the collection time is reduced by mobile LiDAR by 80%. But the challenge is that forest center is worried about because this kind of handheld system costs like 50,000 euros. And the main idea is to test whether it's today, if it's both technology feasible and if it's practically or commercially reliable. This above canopy stuff, this is something what I personally like to continue. It's like a potential holy grail. So what's the added value of that? So you don't get not all the trees. Most probably the quality is even worse. But you can, if you put that kind of sensors, if you have like a helicopter, you can get 1 million reference trees in 1 week. And in Finland it is 3 million reference trees is needed today for country level network, and that is the problem because half of the cost goes there. So it costs almost the same like of course they are using also area-based, but these plots cost the same, what is the national laser scan. Then I go to the topic which is about digital twin and harvester MLS. So not so many people talk about this harvester MLS, but we have been talking about or thinking about for 20 years. In Nordic countries, forest operator or the harvester operator do the decisions. So they decide what trees they will fell, what they leave. In Germany, it's different. In order to know exactly where you are, you need to have a very nice positioning system so you don't cut neighbors' trees. And if you want to select something in prior with a digital map, then you really need to have this kind of few decimeter accuracy. It would be nice to have a biodiversity if there are aspens or some other important trees, there should be leaf there. If there are some damaged trees which are just increasing insect damages, you should remove them. And basically in future, this kind of technology can provide you all the reference data what is needed. But how to do this? So this is the concept what I'm working is that you have a digital twin of forest. It's like our Metsäkanta, or likely even better. It can be also done by handheld laser scanning or whatever you like. And then you have a mobile LiDAR on the harvester, which makes it in real time. And in between you have this kind of 3-to-3 matching. And this 3-to-3 matching, it is like a double system for getting the position, but it also reduces the bias in your positioning. And in MLS, if it's that on a harvester, so harvester doesn't do the loop closures. There is a drift in the positioning all the time, and it increases until you calibrate it out. If you do this kind of 3-to-3 matching, you get rid of that. We have done some mobile LiDAR tests, so first with a sparse, then with a dense. We also have done tests with a Ponce thinning density assistant, which has been like a pre-operational since 2022. And the main idea is that you find the trees of your surrounding, and then you select the trees what you want, and then you know exactly what is the number of trees left per hectare, and the idea is to optimize the future growth. But if you look at this sparse forest and dense forest, you can see from the sparse forest immediately that you see all of the trees in the surrounding. In dense forest, you have problems of seeing the trees even after 10 meters. And we have been especially analyzing that how well you see the trees within 15 meters from the boom or the harvester, because that is the boom range typically. And this is how it works. So if you have a harvester, but in principle harvester is basically staying at the same moment. But this is how you see that if you have a digital twin and you see the trees, what it is and how you can do it. But as I said, the problem is that harvester mobile LiDAR is like a TLS. It's a single scan TLS. So it's problematic to see all of the trees. If you integrate these two technologies, I see that there is a lot of synergies. Like mobile LiDAR, it sees the stem curves. It is like TLS, but it's also ideal for deriving tree count, because it's better for that than the airborne laser scanning. And with airborne laser scanning, if you derive the digital twin there, so you have the biodiversity, you have the species, you can even have a quality. For damage assessment, if you have broken tree tops, it's good. And it also provides like absolute reference. And combining them, of course, I don't know whether this is commercially feasible today, but it is a technique to preserve the biodiversity. As I mentioned, there is a drift always in this mobile LiDAR on the harvester, and you need to calibrate it out. 3-to-3 matching is one technique, but basically you need to do it like in autonomous car. In autonomous car you have an H3 map, and basically then you get an accuracy of between 5 and 10 centimeters. It's the same thing. You don't need to do it at the tree level, but you can also do it at the point cloud level. If you have an airborne laser scanning, even national laser scanning, you can match it. We have certain papers on that, and it gives you 10 to 20 centimeter accuracy, but we have a problem of our reference is like a 10 centimeter accuracy, so it's nice. But this is the way to get rid of that, and you need to have some kind of HD map. It either is at the tree level data or object level data or point level. Related to this harvesting, we have a concept paper where the positioning things are analyzed, and how well you see the trees in the surrounding, how well you are able to measure the trees in the surrounding or the stem curves, and how you can use it in future to use as a field, like a big data for field reference. And I don't go into detail, but I already mentioned that we don't see all the trees, and especially if we are interested to get the stem curve for all the trees, they are even lower number. But basically there are certain tricks that what we do in our system is that we use all the data. I think that the forest companies are doing that way, that they only show the trees which are visible that time. In our system we integrate all the data and we get better results in this way. This tree-to-tree matching, it has been also published, and we actually saw it that this is a feasible concept if the number of trees per hectare is less than 1,800 stems per hectare, which is quite feasible. And in that matching, we are using an algorithm which is very fast. It's this kind of coarse matching which is rotating and translating two maps, 2 tree maps at the object level. And it's very fast. It's a few milliseconds when you do it. And basically, if you get the first match with a digital twin forest map, then the second step is very easy, because you can only move to very, well, just few meters from that. Okay, the possible benefits, but personally I see that the possible benefits are that one is economic. As a harvester operator makes these decisions, it's I mean that in Finland it's 500 million euro is spent every year for forest operations. If you can speed them up by 5%, it's 25 million euro saving. Biodiversity prevention is, I suppose, that is the most valuable. And for that reason, that is already written in our national roadmap, that we should have this kind of system operational in 2035. And we are also now, we have these stem curves, we have a certain toolbox which we are using. We have now improved it computational feasibility. It's now 30 times faster. And we are already doing it in all possible ways. Then I go to tree species. As I mentioned, tree species is one of the key applications for protecting biodiversity, and I think that biodiversity is also most probably the driving force of making these individual tree-level inventories. And what we did is that we did an international benchmarking, so it was very widely used in Europe. We choose to use a multispectral LiDAR because we have one instrument, and so we have 2 data, which was one collected by our helials, which is more than 1,000 points per square meter, and then we have opted Titan, which was something like 35 points per square meter. And we provided data to partners, please process them, and then we see how well everybody can get the tree species. It's already, so this says that it's preprint, but it's already published today, this year on this ISPRS journal, so you can read it. So there are some, 45 authors. We get like 12 different point-based deep learning, 4 image-based deep learning, and then roughly about 10 machine learning methods. So we also compared what is the deep learning, machine learning, and everybody assumed that yes, deep learning should be better, but with very small amount of training data, machine learning should win it. That was basically the assumption. We selected a test site which was a peri-urban or suburban area so that we get these 9 species. In Finland, we basically have 3 species. And these were the species, and the test site was located there. The field reference was collected with a web application developed just for this project. And we had more than 6,000 reference trees. This is an example of the multispectral LiDAR with a dense and the one corresponding tree, what you see it. And this is the same tree with object Titan data and for the whole area. So basically the wavelengths were pretty similar. This is our web application, so it was on the mobile phone. It has, of course it has GPS, but because you cannot rely on GPS on the canopies or there are some buildings. So we had also pre-segmented every tree, and we also had the height information, so canopy height model was included. And the aerial photos were included, and then the idea was that we send the people there and you were supposed to carefully check that whether this is the tree, what is in the map, and if you were sure, then you mark that this is like a pine. Because there are still errors, then we repeat it 2 times. And the last time was done by those who are really expert in that. In addition to these 6,000 trees, so that the reference, we had two different kind of reference. We divided them by crown category, so the dominant, codominant, suppressed trees, and then we have a profile category. So we manually look at every profile, and they were put whether there is a single tree in the segment, whether there is a single tree plus some smaller trees under them, whether there were many trees with the same species, or there were multiple trees with different species, or there were like a part of the tree. So every segment has been classified. So the data it's an open access data, so you can load it from Zenodo, and this is the tree species distribution of the data. We had 11 partners, and basically this is the method. I'm not going into method, but basically the machine learning method, most of them were random forest or modification on that. Related to this image-based deep learning method, we were using, especially there is this, here, this detail view. And detail view was actually winner in the previous tree species competition. But how it was implemented here is that because it was already trained with another data. Nibio, who led this task, was that they used a pre-trained network and predicted these species to our stuff. And then there were some point-based, especially these point transformers and pointness plus. This is for the Helios, for the dense data, so this 1,000 points. And deep learning is in blue, and it win the game. So overall best accuracy was 88%. I believe that the reference accuracy is something like 2 to 3%. So it should be something like 90, 91, where all our errors are there. If you look at the detail view, it's on the other side. It was the worst. But it was because it was pre-trained with a data which is not corresponding Finnish conditions. And when it was pre-trained, you see it in the middle, it's 84%. So it means that tree species classification always requires some local training data. There was a lot of variation in these deep learning approaches, and it was because of different data augmentation strategies. What we also see is that the minority classes, which were rare, deep learning improved them dramatically. So this is a comparison between deep learning and machine learning, how well you get these aspen, rowan, oak, linden, and alder. Related to this object Titan data, which was this 35 points data, there were not any big difference whether it's deep learning, machine learning, and there were almost everybody provided the same accuracy. We also studied that as a function of the amount of training data, and it seems that deep learning would win if the training data would have been bigger. Then we do the scaling laws, and basically on the left side, you see that it was not the case that machine learning is winning deep learning when you have a few training data. We didn't find how few training data there should be that machine learning is winning deep learning. So deep learning was winning, and deep learning was better as a function when the number of segments increased. Then also we studied that what happens to the multispectral data. And it seems that multispectral information, if you have this free channel, it's beneficial, especially if the point density is modest. So modest means something like between 10 pulses to like 50 pulses. So this object titan is an optimum point density for using intensity. And how you understand that is that if you have 1,000 points, so most probably the geometry is different for different tree species. And you don't need so much about the intensity, or the value is less than that. Okay. Then these are actually conclusion of my talk is that this individual tree level, most likely this tree growth, and then this automation of field reference, they are coming into practice, and they are done by Finnish Forestry Center. And it will be like a basic service. It will take some more years for the field reference because they have people, they don't have money to buy the sensors. But most probably we are able to show them that the overall accuracy is pretty the same whether you use manual or our systems. We collaborate with University of Eastern Finland with that. Then there is a research and implementation needed for merging this digital twin and harvester mobile laser scanning data. And we have written jointly with industry a roadmap where we actually clearly said that this kind of product would be needed to protect biodiversity. There is an increasing, so industry, there is an increasing amount of open data, there is an increasing amount of open access methods or deep learning methods, so it's nice situation with industry. You can pick the best out of what is available. Of course, there are some problems nowadays with like this open science in that way that the European security situation due to this Russian-Ukrainian war, it means that we cannot publish all the data as open as we like. Okay, then about this 20 points data. This is the first segmentation using deep learning. And it seems that deep learning combined with an improved point density, it gives you 4 times the number of small trees what was possible with using machine learning and this 5-point data. So there is a dramatic number of small trees now visible in the data. And it also seems that deep learning is a way to do the estimation. So it's it will beat machine learning also in that. So thanks.
About 10 minutes for questions.
Okay. Please, any questions? Not a single question.
I have a question. So what do you see as the primary challenges moving forward using laser scanning to quantify forests? What are the primary data limitations or technology limitations?
I suppose the primary limitation is the, at least in Finland, like forest industry, they like to get free of charge services. So they are used to that government is providing the data. And this is one of the limitations. But there are so many studies showing that if you put €1 on laser scanning, it's at least 10 euro is added value. And there are Annika Kangas from Finnish or Natural Resources Finland. She has studied that if you can increase the accuracy of our forest inventory data by 1%, it saves, at the Finnish level, it's 80 million in total, but the value comes from forest owners, forest industry, it goes to the whole chain. And already this 1 point data was evaluated in that way. I don't know how it was possible, but they said that the added value in the whole process was 50 euro per hectare, which is 1 billion euro in Finland, but that was not annually. I assume that it was something like a 10-year cycle or some cycle. So there is a value, and the biggest problem is that who is paying the data, but society gets a benefit. And it's not a problem actually that we do it at country level, because the data cost is quite low. When Finland started it, if I remember right, it was something like 30 euro per square kilometer, so 30 cents per hectare. And Sweden, when they did it, it was 28 cents per hectare, and now most probably it's close to 50. But it's very cheap when you buy big areas. And industry is still doing it, so it is subcontracted to industry. But the question is how to get multiple actors paying for the data. In Finland it is, I don't remember, but most likely it's 2/3 is paid by NLS, my mother organization, and 1/3 is paid by forestry organization. Then there are some, perhaps 6 other institutes putting something, which still use it quite a lot. And if you can get this 20 points data at the country level, there are more and more applications for red roads, their quality, everything. There are more and more applications possible, but how to get this, you jointly do it. And governments are not so, they are interested in Finland to cut down the costs and not to increase, but this is like a general level, who is paying.
So in the past 20 years, so the individual tree detection starts from like top down, detect the tree top first from CHM, then later on, so as we get like TRS data, so then people develop like bottom up. So now, so different methods has different like strengths and disadvantages. So now, I feel that like now the deep learning is kind of a future. So we train like deep learning models, and so we compare that with different kind of method, and it beats like other methods. So in different forests for the like drone data, and also for the TRS data. Yeah. And so we mentioned that this kind of individual tree segmentation can be moved into like operational status in the near future. So we'll mention this like operational status. So are you talking about like drone data, or is the airborne data? Because right now we are not very confident about the airborne data. So airborne data, so sometimes we cannot even see the tree stems, the tree trunk under the canopy for the airborne data. So our algorithm deep learning end-to-end model has very robust performance on the drone data, but we are not sure about the airborne data. So do you envision that the individual tree segmentation will come into like operational status for the airborne data in the near future? And if yes, so what's the requirement of the point density for the airborne data?
So you mean, okay, I saw this nice example that deep learning is not for airborne data. There is one challenge still. I mean that I mentioned that in 4 days we could process one production block. With the current deep learning techniques, it will take 2 years. So we are not processing even today, we are just processing plots and we are improving the technique. If you are interested in this deep learning, there is from our group Lassi Ruoppa, he published a paper in ISPRS journal. It was benchmarking about different deep learning and he also compared it with machine learning. It's a great paper, please read it. Yes, I know that this urban LiDAR may have complications. It depends on the forest. In Scandinavia, the forests are great. It's the boreal forest, it's more easy. It's more sparse. If you go here out and if you have deciduous trees, it's more complex. And you most probably need to do this leaf of stuff. But if you compare TLS and ALS, they are totally different things. Try to measure TLS for several square kilometers. And then we have in Finland, we have this 300. It's like a one state in the US. It's 338,000 square kilometers. And if you want to, I am dreaming about this kind of scenario that you do country level laser scanning every 3 years. So ALS is the only technique. And then the question is, what is the technique to make the field reference? Of course, TLS is best. It's the best. But is it cost effective for industry and other applications? This is the question.
Thanks for the talk. I have two questions. The first one is to do with law of diminishing returns, and that as you advance the segmentation technology, is there a stage where it gets so good that actually it's good enough for all forestry applications and you don't need to carry on refining it anymore? And the second one was these 700,000 family owners of forests in Finland. Does that complicate the translation of your research into practical use?
So you mean what was?
You mentioned on one of your early slides that there's 700,000 forest owners, and how, in terms of translating all your brilliant technology into practical applications, does that create some problems, or is it?
It doesn't create any problem because it's as I mentioned, it's the state owned, it's the forestry center is serving everybody, and it doesn't complicate anything. So basically, they get this forest inventory free, but they need to pay for the consultation. So now, like 20 years ago, the system was that the stand level forest inventory costed something like more than 10 euro. Now it costs like 1 euro, and it's more accurate. So this is not stuff. And concerning this deep learning, you still need to understand that for the last 15 years, there had not been any dramatic improvement in segmentation techniques. And so it means that the point density is not the way to get the solution. You need to have a better techniques. And I believe that the combination of deep learning and improved point density is the way to go. But you need to have this clever algorithm. And I believe, but it's hard work. It's not easy, but it's hard. And we have tested that the same technique what we have developed for 5-point data. It works, of course, for 5,000 points, but the improvement in accuracy is not that big. It's the deep learning there, but it's hard work. And you need to be careful that you don't get, as I said, there are variability in the outcomes, especially in tree species, but most probably even with segmentation. Yeah, there is.
Could you just speak more the logistics of storing and processing the data? What is your process for storing and processing the data? Like, where does the data live? Where's the processing happen?
So for processing, we have two stories. Like this Metsakanta, we have transferred the tree object. It's running on national CSC computer, so it's a supercomputer, and I can even look at all these 6 billion trees from here, and it's using my phone telecommunication. It works. The problem is transferring data to supercomputers take time. So we still rely on for the processing, we still use this kind of very heavy desktops, we need to find a solution. But I don't think the data amount itself is a problem with ALS. It's a bigger problem with TLS and mobile LiDAR if you have very big areas. And it's actually even bigger if you are work with images. Point cloud are still nice, or LiDAR, it's there. It's a less data in them compared to the images. So I like laser scanning. It's more simple, and I'm simple people, so.
All right, we're up against the break, so let's thank Juha for his keynote. All right, so we have arrived at our first break, but I'm going to orient us to what's coming after that. First off, thanks again to Juha. It's great to get that long-term perspective on a technology that's so central to what so many of us do. All right, so we have a 15-minute break, so we can grab a coffee or a snack. I think they're refilling the coffee now, so if it's not quite ready yet, please be patient. Then after our break at 10:30, we'll head to our first parallel session. We have 3 concurrent sessions, so you get to choose which one you like. The concurrent sessions are on pages 3 and 4 of your conference program. Here in the North Ballroom, we'll have Group A. The 2 other sessions, Groups B and C, are in the Stewart Center, which is next door to the PMU here. You don't have to find a map. We will have some folks at the south end of the South Ballroom who can lead you there. Are Fritz and Desmond around? Okay, they're back there. So Fritz and Desmond will be there to help guide people to the 2 rooms in the Stewart Center where sessions B and C will be. I'm also headed in that direction, so you can look for me and follow me over there as well. And so now, have a break. Thanks, everyone. We're going to try and stay on time, so I'm going to get us going. Welcome back from lunch. Hopefully you all got your fill. We're going to start with our first round of plenary talks. So this session is on advances in remote sensing for forest management. We have 3 speakers. We're going to go one right after the other, and then we'll have time at the end of the session for questions to all 3 of the speakers. So we're going to hold the questions till the end. First up is Dr. Ayman Habib, professor and interim head of the School of Civil Engineering here at Purdue, who will talk to us about ensuring geolocation accuracy of multimodal, multi-platform, and multi-temporal geospatial data. All right, please help me welcome Ayman.
So, good afternoon, everyone. So, as Brady mentioned, this talk is talking about how we ensure the geolocation accuracy of geospatial data, which we get from different sensors on different platforms and at different times. So, throughout the morning, we know actually that traditionally we have our data either from space, airborne, or even terrestrial laser scanning. Right now, we have developments or advances in the sensing technology, whether they are LiDAR, imagery that includes RGB, multispectral, hyperspectral, and thermal, as well as hyperspectral. We have either visible near infrared or shortwave infrared. And then one of the nice things actually is the georeferencing technology, basically, that gives us the position and the orientation of the platform where we have the sensors. And together we have advances also in the mapping platform. So we can have the UEVs, we have wheeled systems, whether they are crewed or uncrewed. We have handheld systems and the backpack units as well. And what's really the key advantage of this, that we have a flux of geospatial data, multimodal, you have imagery and you have LiDAR. You have multi-temporal data. So what you see in the lower right portion is a multi-temporal LiDAR data during the season, leaf off, leaf on, in multiple years from different platforms, UEV, backpack, and airborne. So This is just as an example. This is a plug-in of what we are doing at Purdue. So we are quite active in terms of developing new platforms for data collection. So I'll start from the bottom. So in the bottom, we have the suite of terrestrial LiDAR systems and imagery as well. So we have two wheel-based mobile mapping systems with different grades of navigation and LiDAR units. We have the uncrewed ground vehicle equipped with LiDAR and imagery. And we have the backpack unit that can be either carried while walking, or even you have it on a bike pack or an ATV. And then the top row, we see the airborne systems. So we have the UEV systems. We have two generations, the old generation where we had the payload on a DJI M600 and the newer one on the FreeFly Alta X. And the one which is in the top left, this is actually our newest development. We have a two-seater Sky Arrow systems equipped with hyperspectral in the visible near infrared RGB LiDAR, coupled with a very good position and orientation system. So with this particular system, we are targeting somehow between 400 feet and 2,000, 3,000 feet above ground. So we would like to fill a gap between UEV systems and traditional airborne system. So the summary here is that we have data coming from different modalities, different sensors, different platforms, and at different times. And what you see in the bottom, actually, that you have this basically challenge of how much area you would like to cover as opposed to the resolution you would like to get. So what you see there actually that from space we have very large area coverage, very low geospatial resolution or level of detail. And then as you move to the right and down, you have smaller area covered, but you get high level of detail. And throughout the morning, actually, just basically, can we afford to have very fine resolution at a scale? You cannot do this from a single sensor or a single platform or a single time. So basically, the whole idea is that we would like to fuse, actually, this data from different platforms, different modalities, and different times, so then we can be at the sweet spot. And the sweet spot is basically that you have very large area coverage with very high level of detail. But in order to reach actually this objective or this goal, you have to make sure that this data is basically well aligned or geolocated. So the question is that what does it take to ensure the geolocation accuracy of multimodal, multi-platform, multi-temporal geospatial data? So I always like to have one or two equations in each one of my presentations. So this is what we have here. So basically what we are driving is, at the end, we'd like to have the ground coordinates or points on the ground. So the very nice thing about GPS INS, that gives you the position and the orientation of the platform where your sensors or payload are residing. Depending on the quality of your GPS INS unit, basically the quality of georeferencing or the position and the orientation of the platform will differ. Then you have your suite of sensors, whether it's LiDAR or cameras, RGB, hyperspectral, multispectral, and it's a very, very simple equation. It's just simply a vector summation procedure. So I'm not really going to go through details of what we have in the equation, but the most important thing actually is that basically the categories of the elements we have in the equation. So the first one, which you see in red, basically the trajectory of the platform, the position and the orientation of the sensor as it moves while collecting the data. The second part, which you have in orange, that's the mounting parameter. So the position and the orientation is related to the GPS INS unit. Your sensors are physically separated from the GPS INS unit. And then the measurements from the different sensors. So that's what you see in the blue and the green. So these basically measurements from the sensors, part of it is just like raw measurements. The other part is what we call calibration parameters or internal characteristics of these sensors. So you will not really get good coordinates of the features unless that all these 4 components are well determined. So GPS-INS, if you are working under open sky, it's working well. The mounting parameters, again, depending on how well you do your calibration and how stable your system. And the internal characteristics of the systems, again, it depends on the sensors. Not all the sensors are created equal. Sometimes they are designed to ensure basically the stability of their internal characteristics. And sometimes the stability of the internal characteristics is not really one of the key design requirements, because again, it's just depending on the balance of the cost you would like to invest in buying a sensor versus actually the stability of these parameters. So let's start one step by another, like how we ensure this geolocation accuracy. So the first thing is what we call system calibration. So the system calibration, how we determine the internal characteristics of each sensor, whether it's the LiDAR, whether it's the camera. We call these IOP, or interior orientation parameters, as well as the mounting parameters between your LiDAR, your camera, and your GPS-INS. So we have what we call target-based calibration methods. You have to deploy targets in your calibration test field. You fly, for example, if you have a UAV, and then you identify these targets in your calibration test field, and then you go through an optimization process where basically you would like to identify the individual targets in the individual tracks or flight lines or individual walks or drive run. And then basically you try to optimize the mounting parameters, the interior orientation parameters, to make sure that all these things fit together. So that's what we have in the bottom row before, where you see ghosting or different versions of the same calibration feature, whether it's a hut, for example, or the ground or building facades. And then you have the other part is after the calibration. So this is basically, if we have a very good system, well built, you do this only once. So then once you determine the interior and the mounting parameters, then you are set. The problem is that sometimes if the systems are not really designed for this very precise mapping applications, we have to do the calibration more than once. So this is actually, there's a motivation to do what we call in situ or targetless calibration, because deploying the targets, figuring out that how you have a very good calibration test field is not really practical. And sometimes even you have a good sensors, but then an accident happened, you drop the sensor, so you have to do the calibration another time. So this is a motivation where we are trying to do targetless, or what we call in situ system calibration. And one of the things we are working on here, how we develop a generalized calibration framework that can handle data from airborne systems, from UAVs, whether it's crewed or uncrewed, and from ground, like for example, our backpack. And because it's targetless, we have to rely on the features we see. So this is what you see on the right, some of the examples, what kind of features we can use in a forest environment. So in a forest environment, we can see the ground, we can see the trees, the tree trunks, and the branches. So those are actually the primitives or the features we use in the optimization for the system calibration. And in the lower right, you can see some example where we extract ground patches and tree trunks, and this is what we are used for the targetless system calibration. So I'm not really going to go through this details here, but again, the main part here is that, again, your data will not be good unless you have the trajectory well-defined and the system calibration. And like Juha mentioned this morning, you can have actually SLAM techniques that gives you well-positioned point clouds in a relative sense, but the SLAM will always drift. So as a result, actually, because of the drift, things will look relatively good, that you will see very well-defined tree trunks. However, the drift will change with time. So in order to really reduce the amount of drift, and you have mentioned some of this, you can use existing data. So one of the things that we did in our actually system calibration is that if we have legacy data, like for example, 3-depth data or data from another platform, we put this as part of the system calibration, and at the end, we ensure that our optimization more or less maintains the same absolute accuracy of the legacy data or the geospatial data. So that's basically what this flow chart is doing. So this, so far I have been talking about LiDAR access. So just to give you an example, this is an example of our latest data acquisitions from our airborne system. It was, I think, maybe sometime in April. So this is just a profile in Martel Forest. So here we have different tracks. We have 4 tracks in different colors. We have also DTM. This is derived from Digital Elevation Program, the 3-depth data. So here we are talking about data sets which are almost 7 or 8 years apart. So if you put all these data sets together, you can see that they look more or less okay, but you can see in the XY, you can see discrepancies of up to 1 meter, and in height, you have discrepancies like half a meter. But after you do this proper system calibration, you can see that everything is much better aligned. So in this case, actually, we ensure that the data here, which we have like 8 years apart or 7 years apart, are very well aligned. So I'll just go again. This is before the calibration, and this is after the calibration. You can see features are becoming more well-defined. So another part here again is that here I'm talking about LiDAR. You have LiDAR and imagery. You have to make sure that you put them together as well. And without getting into technical details, again, you have the imagery data is 2D, you have the LiDAR data in 3D, and you would like to do the system calibration by integrating 2D data and 3D data. So there are 2 ways actually to do this. Is either you take the 2D data and make it 3D and try to align it with a LiDAR, or you take the 3D LiDAR data, you make 2D imagery, and then you try to align it. So these are basically 2 different approaches to do this. The only problem, if you would like to take the 2D imagery and create 3D data, you have to have requirements on the imaging system that has lots of overlap to do structure from motion. So we have actually these 2 approaches, what we call 2D to 2D or 2D to 3D or 3D to 3D, depending on the modality of the system, whether you have cameras with high frame rate or not. And we developed these techniques actually, and this allows us to make sure that the imagery data and the LiDAR data are well aligned. And each one of them, they have pros and cons, but we have both options available. Just to give you an example of what does that mean at the end. So what you can see on the top row actually is that we take the LiDAR data, these are the red dots, we try to back project them to the imagery. If the calibration is good and the trajectory is good, the LiDAR point cloud, which is red, should project exactly where they are supposed to be on the imagery. So here we are looking at 3 trunks. So you can see in the first row is basically they are relatively well aligned, but we have some deviations between the 2. The middle row, when we adjust the system calibration, you can see we have an improvement. The third row is basically we do what we call trajectory enhancement, so we even refine the alignment. So this is actually the ultimate goal here, because if we do this well, the system calibration and trajectory enhancement, we can identify a tree trunk or the geometry of the tree from the LiDAR data. The spectral information comes from the imagery data, and you know that this particular object in the LiDAR data corresponds to this particular region in the image data. So now actually things will come a little bit, the trajectory. The problem with the trajectory, if you collect data under canopy, then you have actually these issues, GPS signal outages, and then it's not only the system calibration, but the trajectory enhancement. The nice thing actually, or what you see here in the lower right, is that if the GPS trajectory is not good, you can see this ghosting of the LiDAR point cloud data. So we develop what we call TEAM, trajectory enhancement and mapping. We don't use the SLAM because in the SLAM mainly deals with aligning the data in a relative sense. With TEAM, we are quite interested in aligning the data in an absolute sense. So just to give you an example, so what you see in the upper left, the data from the backpack LiDAR if you have problems with the trajectory. You see this ghosting. If you use a SLAM or SLAM-like technique, you will get what you have in the top right. Relatively, in a relative sense, data looks very nice. You can see the 3 trunks are well defined. However, If you take this data and try to align it with the UEV data, you will get what you have in the lower left. We can see in the XY we have 1.5 or 1.2 meter difference, and in the Z you have 2.5 meter. So if we use actually our team where we fuse the data sets together during the team optimization, you get what we have in the lower right. And that's actually very, very important to make sure now that the UEV data and the backpack data are well aligned. So this is the same thing here. We are showing an example with the backpack data in Purdue campus. Again, here we have in the top left, basically you have misalignment because of issues with trajectory. When you do the slam like, you get well-aligned data. But now here we have multiple data sets. We have Geiger mode data over the campus. So on the lower left, you see some discrepancies of 70 centimeters to 40 centimeters. And if we do this properly, we have very well-aligned Geiger mode data with basically the backpack data. And those data sets are 4 years time difference. So in conclusion, actually here, why do we care about geolocation accuracy? Juha mentioned this morning that one of the most expensive approaches or things or activities is collecting reference data. So by having actually this backpack and UEV data, you can collect reference data to calibrate and update or more or less models you have for airborne data. So these are just some of the examples, like upsampling networks. If you have training data from backpack, UEV, airborne, this is geolocation accuracy is very important. Past planning as well, having an idea about having UEV data and how you design your backpack model to get the best trajectory, that's another example or need. The semantic segmentation as well, training the model to deal with multiple data sets from different platforms, different modalities at different times. That's very important. And this is just the last example I would like to show here is that now you can have universal model that can handle basically data acquired from a top view perspective or bottom view perspective. And again, if you merge the hyperspectral data, the RGB data with the geometry data, you have the best training approaches for species identification. So in summary, actually what I wanted to say here is that we have flux of data. I'm a bit biased, but I believe that you cannot take full advantage of this data until you merge all these data sets and you ensure that well aligned. Thank you very much.
All right, thank you, Ayman. Next up, we have Professor Youngkin Song from Seoul National University, who'll be talking to us about individual tree and area-based regional carbon stock mapping using high-density airborne LiDAR, a case study from Gyeonggi, South Korea, sorry, just a little bit different.
Hello everyone. Now it's the midnight in South Korea, so my head is a little bit dizzy. Okay. Title here, my mistake. So the correct title is, as Brady said, individual tree and area-based regional carbon stock mapping using high-density airborne LiDAR, a case study of Gyeonggi province in South Korea. So this is not as kind of the completed research. This is kind of the introduction of current our project. So I want to discuss about the challenges and opportunities in this project. I think all of you already know about the NEON project. I have not. So based on my information, NEON project in US is for more than 20 typical ecosystem sites and conduct LiDAR and remote sensing data analysis for more than 100 square kilometer per site. Is it correct? In this project, we include various ecosystems, forests, urban areas, agricultural lands, wetlands, coastal ecosystems, and so on. But our site covers more than 10,000 square kilometers as one continuous landscape and across 31 municipal governments. So this project is actually for making so-called urban ecological maps. So designed by law and for supporting the carbon offset program in this province. So what are the urban ecological maps? So since 2019, every city government in Korea should prepare and use this map in many environmental planning issues. So this map is the vector-based polygons and not raster, and are categorized into more than 2,000 types of local ecosystem. So you can see it was made in very detailed typology in each type. And also it includes many different ecological layers for more than 10,000 square kilometers. So all these items are fixed in the law, and one of them was the carbon stock. Yeah, so I will explain about that. So we cannot do this kind of making map work only by the field work. So many remote sensing materials were used, and including airborne LiDAR dataset. So all different geosurvey companies carried out this mission with their different instruments and different reasons. So we asked for the high point density, so it was not easy to follow this kind of directions. So as you can see in this cross-section view, the point density is quite high, enough to describe the detailed topography and the shape of individual trees. So quality check was an important stage because different companies in different places must show the same quality. So this was the whole flow to derive the vegetation carbon stock for each biotope area. So first, classify the ground and non-ground, and vegetation and non-vegetation. And second, get the canopy height model. And third, clip the point clouds by the biotope polygons. And fourth, get the individual tree heights and DBH and within each polygon. And lastly, derive the above ground biomass and carbon stock. That this is simple and well known, but never easy for the more than 10,000 square kilometers. So first, classification. So I won't talk much about this stage, but it was still challenging. Even with we have a lot of built-in programs in the air surveying tools. So there is no universal algorithm to classify it perfectly. So it requires a laborious checking the process by engineers. And next, point cloud clipping. So it was not easy to clip the more than hundreds of terabytes of point clouds by about 2 million biotope polygons. So it was necessary, but it was necessary to run the individual tree-based processing later. So we basically worked by the map frames. Map frames more than 2,000. So a lot of the linear polygons in here, like rows, were across the frames. And many polygons were located across the frame borders. So we had to evaluate those attributes and decide how to aggregate them into one polygon across the borders. And there are many donuts, the polygon within a polygon, which requires additional processing beyond the normal clipping. And next, we should estimate the number of individual trees and their heights by detecting tree tops. We know there are a lot of uncertainties, especially in deciduous trees and in irregular shaped trees like this. Yeah, and it was a lot, so that kind of uncertainties were a lot, especially in the sloping terrain with the uncertain crown sizes. So how to get the range for the local maxima or local minima was critical. So good case, there was good cases, and bad cases, poor cases were mixed. Especially on the slopes, trees grow not vertically, but treetop detection usually works top-down, so which makes the wrong results. So there were some good cases, and poor cases were mixed. Another huge the uncertainty was detecting the sub-canopy mid-sized trees. So to mitigate this problem, we assessed the vertical canopy structure carefully, not only by the absolute height, but also the relative height. Please check my students' the poster to dig into these issues by publication. Yeah. So one example. You can see the below, we had a very detailed vertical canopy structure along the detailed topography and polygons. So we use this kind of information to add the sub-canopy middle-sized trees in calculating the above-ground biomass. Next, we had to develop our own height and DBH relationship equation and biomass allometric equations. The most challenging part was to estimate the DBH from the heights from the canopy height model. So in the classical field survey, we measure DBH and then estimate the height. But with the LiDAR, it works the other way around. So we cannot use we cannot use the inverse function, the height to DBH, DBH to height. So there are many the over and under estimation issues because no empirical model is perfect. So we already had, already had those equations in forestry, but there are some issues. The previous equations in forestry developed based on the NFI, National Forest Inventory, long-term monitoring sites. But in this project, we should process over continuous landscapes across forest and non-forest areas. So NFI cannot be the representative across these regions. So we took the terrestrial LiDAR data set from about 200 sample sites, and we made our own ground truth of key metrics for 3 attributes and got the relationship with airborne LiDARs. This is how to get the TLS, the data sets. And we kept many individual trees considering the species variation in this region. If you see the height and DBH relationship, the distribution of many circles is different from the triangles, meaning that the forest and non-forest trees should be separated. Okay. The purple line, the urban trees exhibit a larger DBH at the given height than the green line, the forest trees, meaning that the wider spacing and active crop management and lower competition. And the trend was quite obvious in all types of the major species. So of course, there are more variations when we consider the heterogeneity of land cover types. But at least we should separate the forest and non-forest cases. So we developed the height and DBH relationship in forest areas and non-forest urban areas. And I did not explain detailed, but we developed the biomass equations in forest areas using from the TLS and non-forest urban areas separately. R-scale and error range was varied, but I think they were acceptable overall. And lastly, we put one number for each item, I mean DBH and height and biomass into one built-up polygon. So we do not input the raw or individual tree-based information. So I think there are a lot of accumulated uncertainties, but for this, the process we can reduce by the aggregation. So as you can see, the representative mean number were used in the final official output. And finally, we made a regional scale, the canopy height model from the high density airborne LiDAR dataset. We successfully derived the inventory of this kind of inventory by biota types and the species across this region. This is an example. We provided the vegetation carbon stock not only in the urban, not only in the forest region, but also the small urban canopy patches. I think that is enough to use the carbon offset program later. Now we are exploring what is the interesting in this kind of results. So quercus and the pinus species were dominant in this region, but those are not always the tallest trees. And many species and local-based approaches will be possible, like this. We also compared our result with the NFI, National Forest Inventory results. Overall agreement is acceptable, I think. But some variations are expected because ALS airborne LiDAR dataset sees from the top, but whereas the national inventory sees from the bottom. So I have been working on this kind of LiDAR research is more than 20 years. So we already know how powerful the airborne LiDAR can be, and we have seen many wonderful examples. But the processing more than 10,000 square kilometers across diverse landscapes within one consistent analytical framework, I think that is a completely different story. So I would love to hear your experience and ideas on how to overcome this kind of the challenges. Thank you.
Thank you, Yunkin. That was great. Okay, so we're going to shift now from carbon mapping towards long-term forest monitoring and change detection. Our next speaker is Carlos Silva, who's faculty at the University of Florida.
Okay. Good afternoon, everybody. Thank you very much for the introduction, and thank you for the invitation to be here. We are excited to be here. I guess this is my first time at Purdue, and also my first time in Indiana. And I heard that Indiana has the best root beer in the country, so it was exciting to hear and try out. So today I'm not going to talk about root beers. I'm going to talk about LiDAR and remote sensing, how we're using remote sensing AI to map impact of hurricanes in Florida. So as you all know, we're a new area of remote sensing technology, right? We have a bunch of sensors in this space. As you can see here, we have the NASA ISAT-2, we have JEDI, we have NISAR, we have sensors on the ground. This is me 4 years ago, 5 years ago. We have airplanes flying over. This is my friend, Dan Hayes. He has his sensor in his airplane. We have UAVs flying out over. Oh. And I guess the challenge is not the data availability anymore, it's like how to integrate the data and translate to useful products so the stakeholders can use. We can collect data every second that I'm talking here, someone is collecting data somewhere. So I guess the problem is not the data sets anymore, it's how to integrate and translate to useful product. So here you can see a beautiful LiDAR 3D point cloud, right? We have been talking about LiDAR since in the morning. So LiDAR provide 3D information of the forest. We can go from a point cloud, a raw point cloud, to leaf and wood classification, and then the QSN models that we can use to estimate volume. I get so excited with LiDAR, so I teach LiDAR remote sensing in Florida, and then sometimes I get too excited that in addition of scanning forest, I like to scan my students. So those are my students from Forest Mensuration a couple years ago. And then in addition to my students, my friends, my professors, they get mad because I was scanning the students, so I decided to scan the professors as well. So you can see, we can do a bunch of things with LiDAR. But today, I'm not going to talk about how we're using lasers to scan people. I'm going to talk about how we use lasers to scan forest. Forests are not static, it's dynamic, right? You can see here a point cloud collected from airplanes before a disturbance event. This was a hurricane 2018 in Florida, so we can have a beautiful point cloud, and then we can have a disturbance event. It's a hurricane coming. So after the hurricane, we can go back and scan again, and we can see the impact of the disturbance. So here we can see that the chemical cover dropped from 80 to 30% after a disturbance event. So it's really important for us to not map forests only one time. So we care about mapping forests through time. So that's why we introduced the concept 4D, which is very basic, is 3D plus time. So moving forward on my presentation today, I'm just going to give you an example how we're using remote sensing to map forest over time in Florida. So this is one of the NASA projects that I have funded from the ISAT-2 program. So here we're using ISAT-2 to map forest disturbance and recovery over time. So this is the NASA ISAT-2 LiDAR mission. How many of you have heard about ISAT-2 here? Okay. So ISAT-2, it's an amazing sensor that has been out there since 2018, collecting data. We can use ISAT-2 to measure forests. Initially, it was designed for cryosphere and land and sea ice, but we can use ISAT-2 for vegetation as well. So ISAT-2 uses a green light instead of an infrared. And then here is how ISAT-2 collects the data. So this is an animation for about 1 or 2 days. By the way, I just developed a new R package for ISAT-2, and this animation can be done on the R package, so I just did before coming here a couple days ago. So this is just 1 or 2 days of data collection. As you can see, it's almost like a global coverage. So ISAT-2 operates with 6 ground tracks. They are combined in pairs of 3 pairs, and they are spaced by 3.3 kilometers. ISAT-2 uses strong and weak laser beams, and then we have a diameter on the ground about 10 to 12 meters, and then from that we can create a beautiful photon cloud, like a 3D point cloud, X, Y, and Z. And then with that point cloud, we can classify the noise, the ground, and the vegetation. Once we classify the point cloud, we can then extract the information that we care, such as canopy height, canopy cover, and so. So hurricanes are one of the major disturbances for us in Florida. I'm originally from Brazil, and I have been living in Florida for 5 years. So every year we have alerts of hurricanes. So then I decided to start studying hurricanes, how can use remote sensing to map the impact of hurricanes. So this is a Hurricane Ian back in 2022. I was already in Florida when this happened. You can see that it caused a lot of damage, not only on the city, but also in the forest environment as well. So here was Hurricane Michael back in 2018. So this is the one that I'm using for my project. The Hurricane Michael was a Category 5 in the Panhandle area and destroyed a lot of the forest that we have there. And then after moving to Florida and start working with hurricanes, and after our first hurricane season, I decided to study more about hurricanes. And the first thing that I want to do was to produce a map like this. And this is a very interesting map, but also very scary. You know why? When you look at the map, you see that it shows the return interval of tropical cyclones, and then I took that map and I overlaid with the biomass map. You can see as you go from gray to blue, more hurricanes are coming over time. You can see that it goes from 10,000 years to 1 year. So, and then you can also overlap with biomass. You can see that it goes from 0 to 200 tons per hectare. You can see that where we are living in Florida, we are going to have hurricanes every year. and it's going to affect most of our forest. So after producing this map, I came back home and I told my wife, hey, let's take the boy and let's get out of Florida because we're going to face hurricanes every year. And that's crazy. So this is one example of the hurricane. Catastrophic damage, destroyed the entire forest. And then here's how we're scanning our forest with VZ400i. This is a Rigo system that I have on my lab. It's really hard to measure the trees after a damage, so we're scanning in 3D. And then on this animation, you can see all the kind of damage you can get. We also developed our package called RTLS Deep a couple years ago. You all can try. And with this package, you can process the point cloud and classify damage severity using deep learning. But those are the kind of damage you can see after hurricane disturbance. So in this NASA project, we are interested to quantify the impact of hurricanes and using ISAT-2, integrated with Landsat and Sentinel, and of course AI. Unfortunately, we don't have a lot of data sets, so we can only assess short-term recovery, but also we are integrating all the maps that we're producing with ecosystem demography models so we can make projections to the next 50 and 100 years with different scenarios of disturbance. So ISAT-2 is a sampling system. It does not provide a wall-to-wall product. So we're not going to have a wall-to-wall canopy height map at 1 meter, 10 meter, 30 meters. We need to integrate ISAT-2 with other sensors. Right? We can integrate ISAT-2 with Landsat, with Sentinel, with whatever sensor you have wall-to-wall data you can integrate. And for that, we developed an approach back to 2021 when I was working in Maryland, University of Maryland. We developed a framework to integrate ISAT-2, JEDI, and ISAR. So for this NASA project, I'm using a similar approach to integrate ISAT-2 with these other sensors that I just mentioned. So first, we start with a sparse ISAT-2 data set. Right? We can estimate canopy height at 30 meters. And then you can see on this illustration that in the area, there is a lot of empty space. So that's not what the land managers, they want. They want to have wall-to-wall maps, right? So then we can use the sparse canopy height estimates from ISAT-2. We can integrate that on an AI model. Here I'm just illustrating a simple random forest model that worked well for us, but we're testing deep learning approach as well. So once I develop my model, I can then apply across the landscape and get wall-to-wall maps, right? Once this framework is developed, I can apply over time, and then I can get change in terms of canopy height, canopy cover, and so on. So here's one example of the products that we produced so far. So here are canopy heights from 2018 to 2024. The maps are estimated at a spatial resolution of 30 meters. It's a map per year. Here's just a figure that illustrates our bootstrapping validation. We got R squared almost 9.7, 0.9.7, RMSE about 10%, and bias really low, less than 1%. But of course, the project is still going. We want to validate in more areas. We are going to collect more lighter data to do an external validation as well. But with those products, we can start to see already the impact of the hurricanes. So here's a nice example in one of our sites in Georgia. So if you can see that the canopy height on that area before a disturbance event was about 22 meters. But after the disturbance in 2019, it dropped drastically. You can see what happened on the area. From 23 meters, it dropped to 10 meters. So what more interesting than see the disturbance is the recovery trajectory. You can see that after 5 years, the forest recovered a little bit, only like a couple meters, which is expected. So as I said, like unfortunately, we don't have enough data sets to go over like 10, 20 years of data set to the future. So that's why we're integrating this product with ecosystem demography models so we can make projections to the future. And I don't know much about ecosystem demography models. This is a new thing to me. I have my collaborators there work with me, but I'm also developing our package to run ecosystem demography model, because that's a thing that I like to do. So here's another example of the product that we produced, the damage severity. You can see along the hurricane path, we have the catastrophic damage, which basically show the forest that we lost more than 50% of canopy height, followed by the severe, moderate, light, and no damage. And then here the resolution is 30 meters, spatial resolution. So as I said, all this pipeline that we use on this project is available for free for you guys. I have been doing this for more than 10 years. Like all my projects, I like to develop our package. Those are not very good package, by the way, but I like to make available to the community, and I like to interact, and I have a lot of comments and edits that help to improve the package. In this package, you can do all the framework that I just mentioned. You can start with the ISAT2, you can integrate with the optical data, the SAR data, and develop the upscaling approach. The nice thing about this package that you can work locally, but it also integrates with Earth Engine, everything in R. So you don't need to download data from Earth Engine on your machine and do all the modeling and upscaling approach. Everything is connected in R. So as I said, the package is available on GitHub. We submitted to CRAN a couple days ago, so hopefully it will be available on CRAN as well. And then here, as I said, how we're validating, this is Dr. Bueno, one of my postdoc. Here's the strong guy in the lab. So here's the one that carried this laser, because this is one of the best lasers in the market, I would say. Rigo VZ400i, you can see the point cloud with high resolution. I have a student that she's like mapping and estimating the angle of the branches for plant phenotyping. You can do that with that system, but if you're doing field work over a week and working like 10 hours day in the forest, you cannot do that. You cannot carry this system the entire day. Otherwise, you're going to hurt your back. That's what happened with me, so that's why I have younger people in my lab helping me with that. But that's how we're doing it. So to help the stakeholders and make our products available, we're not just producing maps and our package, we're also producing platforms that allow the stakeholders to access our products, and we like to have this feedback. We want to have like inputs from the stakeholders as well. Just like 3 years ago, or 2 years ago, I had a stakeholder workshop in Brazil. We had almost 500 people attending the workshop, and it was really nice because, you know, we can show here really beautiful pictures or videos of the lidar, but sometimes it does not work in the reality for the stakeholders. So it's really important to see, to get their opinions as well. So here, as I said, there is this platform available, and then there's a short animation. So this is just the beta version. We are improving, but you can see we have maps from 2018 to 24. You can zoom in on those maps. The color does represent height. The yellow is the higher heights. Blue is the low height. So you can come here, you can draw a polygon on your area, or you can upload a shapefile if you have a shapefile, and then you can extract metrics relating to that product. So right now we are developing a report, so the users can click and get a report for their area of interest, and also they can see the recovery over time as well. So as I can see here, you can draw a polygon, you can get the height estimate, you can change the layers, and then this is available for all the area of interest, but also we develop a kind of height map for the entire southern US, and the product and the paper is in review right now, and hopefully soon will be available. And instead of producing at 30 meters, we produce at 10 meters using ISAT2. The nice thing about this R package that allows you to reprocess the ISAT2 and come up with kind of height metrics at whatever resolution you want. Of course, you don't want to produce maps at 1 meter resolution, 3 meters or 5, because you might not have enough photons on that resolution. But we tested it, we were able to get at least at 10 meters, a good amount of photons to produce the map at 10 meters spatial resolution. So after producing the maps and get the damage severity, we summarize the damage severity by county. So you can see here the catastrophic damage by county, the severe, light, and no damage. I think this is really important for the stakeholders, for the government agency, for insurance claims, and silviculture operation that need to be done after a disturbance event. I guess that's what I've had prepared for today. Thank you very much. I'll be glad to address any question.
Okay, so at this point, we'll open it up to questions for all of our speakers, and maybe we can ask Young-kun and Simon to come back, or Iman to come back up. Sorry, I need a coffee apparently. And we can have questions for all three.
Hi, I'm from Purdue AI. So as much as AI is a mystery for some people here, forestry is a mystery for me. So I have some questions, and I hope they are not that stupid. The first question is from you. So some part of your talk, you had multimodal fusion. I want to know that which method you used over there.
That was for me?
Yeah.
Okay, great. Thank you for the question. Yes, we are combining ISAT2 with Landsat and Sentinel. So for the fusion approach, we're just doing, like, as I said, like AI. You're using random forest model. We start first with the ISAT2 data at 30-meter segment, and then for the same area, we have the Landsat and Sentinel. So then we develop the upscaling approach, like the model. Once the model is calibrated, we just apply on the Landsat and Sentinel data. So we're not combining, like, the combination is through modeling.
How is it? Did you use CNN, like convolutional neural networks?
Yeah, as I said, like for this simple example, we're using random forest, but yes, we are testing UNet, we are testing ResNet, and many other deep learning approaches. Like we are starting talking about foundation models now, how we can integrate foundation models in this framework as well. But for now, I just had 15 minutes presentation here. We just use random forest just to illustrate how we are doing the upscaling approach. But on the publication that I mentioned that we published in RSE, so that described the entire workflow. So I can talk more about that if you were interested. And also the R package that I developed, you can do that. Like you can go to the GitHub page, copy the code, and run your R. You can come up with a wall-to-wall map that you can apply over time. It's available there, so you can do it.
Yeah, one suggestion is like with CNNs, like imagine an image has 3 channels of RGB, then all the visual data can be attached to the end of it, like you can have many channels and pass all of them at the same time to CNN. Yeah, some of our collaborators in other projects, they are using this kind of method.
Yeah, exactly. Yeah. Like for us, we are producing about 600 layers from this ancillary data set for the modeling. So that's exactly what you're talking about. If we have these layers, how can we combine to produce the wall-to-wall map, right? For my example here, I just use random forest, but of course we can use UNet and CNN models.
I can ask one more question. You can pass. Oh, so my question is for Ayman. We have some projects with other departments in Purdue. So most of the time, we claim that sometimes data collection is more expensive than AI processing. So we can make AI collection cheaper, the data collection cheaper, and then AI processing more to regenerate some data. For example, you can collect all 2D images from whatever you want and do the 3D processing using AI instead of using LiDAR. I just want to know that how is in your field, is using LiDAR cheaper or not using LiDAR, just do 2D data collection and then generate the 3D data using 3D reconstruction methods?
So when you talk about 2D and 3D, you're talking about image-based 3D reconstruction.
Yes.
So, I mean, yeah, like one of the nice things about LiDAR actually, or like let's say with the 3D imagery and then you go from imagery to 3D products, you can get the outer envelope very nicely.
Yeah.
But I mean, if you are really trying to get some information inside the canopy, that would be very hard to do with imagery. So that's what I would say. LiDAR actually is more or less very, very good actually to give you the canopy, the ground, and somewhere in between. The level of detail depends on the point density. So what I would say is not really just saying using the imagery and trying to go from imagery to 3D. Let's say that one of the advantages of AI is that you can use LiDAR. You have actually sparse data, and then if you have enough training data, you can do upsampling or super resolution of the LiDAR data.
Yeah.
That's, I would say, is really better. So I would not really say that imagery could replace or could really do something similar to what the LiDAR. But doing this upsampling or super resolution of LiDAR data going from low density or sparse to high density, if you have enough training data, then AI will do a very good job there.
Yeah. We have some other projects with civil engineering department in Purdue, and they do like 2D in different applications, and then they do image stitching to generate the whole platform from 2D images. So that's why this question came to me. Thank you. Thank you.
Other questions?
For Dr. Soon, I would or song, sorry. Wondering if, well, when you're doing the allometric equations, did you see significant variations within species across the range or spatial variation within species?
Sorry, your question is about our own equations? Yes. Actually, we had already the kind of equations, but actually, the purpose of this project is for the decision making, which means we can make many maps, but that must be really, really accurate because this project is for the carbon offset program. So if we develop a area, we accurately calculate how much carbon we lost, so that kind of thing. So we need more accuracy. So that is why we develop by ourselves. Yeah. Thank you.
I've got a question for Eamon, and it's related to during lockdown, a friend of mine collected global, freely available airborne laser scanning data sets and put them into a big database, and which is amazing. And he's been trying to analyze these, and we've corrected for point density and scan angle and all those differences between surveys. But I wondered from your talk whether you could retrospectively look at a data set like that and do the geolocation better. Can you work retrospectively with your techniques, or do you need to, plan in advance when you're doing new surveys how you are going to align the different data sets?
That's a very good question. And our approach actually basically, it takes all the data sets together and does a single optimization. And it is your decision to decide which one you trust most, and you say, this is the one that I will use as a reference. So for example, when we did the stuff with the Geiger mode or the UEV data or the 3-depth data, we put them all together. And for example, we use the Geiger mode, which we collected, which is 21 data acquisition. We say, this is really the reference, and we adjust everything to this one. So basically, you decide which one, the one you trust more, and then we'll make everything fits to it. Hopefully I answer your question.
No, that sounds good. So as time progresses and we get higher point densities in laser scanning, you would go for the more recent one and try and align it with some sort of rubbish one from 15 years ago. Okay.
Okay, we are at exactly 2 o'clock, so we are at the start of a 15-minute break, and then we're going to go straight into a poster session. The posters are upstairs, and so I encourage you to grab a coffee and head upstairs. We will resume in this room at 4 o'clock for our second plenary session. Thanks, everyone. Okay, let's go ahead and get started. Welcome back, everyone. I hate to cut short the great conversations that everyone was having on the posters. So if you didn't get a chance to view all of the posters or a chance to finish your conversation, the rooms upstairs will be open through lunch tomorrow, so you'll have plenty of time to peruse posters and talk with your colleagues. All right, we'll also have more time to chat with the exhibitors at breakfast tomorrow morning. And so now I'm pleased to introduce our next plenary session. This is going to focus on forest health, resilience, and climate applications. We're going to bring together plant biology, digital technologies, and landscape scale resilience approaches. Our first speaker is Professor John Couture in entomology and forestry here at Purdue University, who's going to talk to us about combining digital approaches and plant biology to monitor forest health. Let's welcome John.
All right, everybody. Very happy to kick off this afternoon session. Should it be down here as well? On the floor? No? Oh, okay. So we're going to talk about how can we combine digital approaches how can we combine digital approaches and basic plant responses to stress from a chemical and physiological standpoint to monitor forest health in this application? So the idea of digital forestry is one that has, admittedly, it's lagged behind in terms of incorporating precision agricultural approaches into monitoring for plant stress. And the challenge is that you have multiple different spatial scales. You both have the spatial scale of horizontal, so the distance, and you also have the height, right? Flying over a row crop for corn is somewhat simpler than flying over a forested system. But remote sensing has the potential to resolve many of these challenges with integrating precision agricultural practices into forestry. And it's not new. Remote sensing has been used in forestry for a long time. When I was at the University of Wisconsin, Ken Rafa would tell me, his first job was monitoring spongy moth defoliation using aerial imagery. So this isn't a new idea, but the applications that we have and the data that we're able to collect have advanced in that sense. There still are some questions about how do we completely integrate precision agricultural approaches into forest systems to, in this particular use case, understand forest health. So the main form of sensing that my group does is spectroscopy. We use full-range hyperspectral data, and spectroscopy is, at the basic input, is just the way that light interacts with the substrate. It's been used in geology forever to understand mineral composition in rocks. The applications we use are for how can we understand plant health. So based on the absorption, transmission, or scattering of light, you can get an idea of the chemical composition. And this is what I always have a green leaf on this one because it tells me that this is what a pretty general green leaf reflectance profile looks like. And what we can see is that changes in spectral profiles are typically related with either genetic variation, changes in chemical composition, changes in physiological processes, and they can give us an idea of how plants are responding to certain environments. Interestingly, much of the information that we need or is contained, it's outside of what we can see. So if you see I have a little blue, green, and red indicator, that's what we can see. That's the idea I think this group knows. That's kind of what your phone does. It captures a picture in a number of different, it puts in percentages of color, and then you get a rendering of an image, right? But you also have, in addition to the visible wavelength range that we can see, which is related to quite a bit of pigment-based biochemicals, you have the near-infrared, which is strongly related to intracellular structure, things like palisade parenchyma length or cuticular layer, and the shortwave infrared, which also has a number of water absorption features and secondary metabolite biochemical absorption features as well. The nice thing about spectral data is that if you scale it, it looks generally the same, right? It's not going to look exactly the same, but it's going to look generally the same. So if you look at what we, and my group usually works at proximal or leaf level measurements because it's exceptionally controlled, but if you look at what you see at the leaf level measurement and you start to scale it up to a canopy level measurement, it looks similar, and you go all the way up to an aircraft borne measurement, something like from Avarice, you can see that the general structure looks the same. So what does that mean? That means that we can start to scale these measurements. So if we can collect enough calibrated spectral data, we can start to scale across these different resolutions to bridge gaps, right, in terms of our understanding from leaves to individual plants to landscapes, right? And that's truly the benefit of spectral data. It's one of the only forms that can scale at this particular level. How do we use these data? My group uses them predominantly in two different ways. One is spectral phenotyping, which is where we look at kind of the cumulative variation in spectral data across different wavelength ranges, and we use statistical methods to separate them out. So is something different from a control? Is something different from a stress plant? And you can see that there are changes in the reflectance profiles that are induced by stress that you can then use to statistically separate these out in spectral space. The second way that we use these data are by functional trait estimations. And what I mean by that is that all of the biochemical, physiological, physiochemical measurements that plants have going on in general, we can estimate a large number of these parameters using spectral data. So if we look at our green leaf spectral measurement, the reasoning that we can actually do this is because we know that there are chemically important absorption features scattered throughout the spectrum, whether they're related to protein content, nitrogen, water content. My group does quite a bit of work with secondary metabolites, but we can exploit these absorption features and the variation in the spectra that we can pair variation in spectral data with variation in functional trait data using statistical approaches to get a predictive model where we can estimate these traits non-invasively, and we can say we're going to predict a suite of traits in this plant based on the spectral data alone. So if we link this all together, what this allows us to do is to start to develop a filter-based monitoring approach, right, at different platforms. So we can use both spectral phenotyping and functional trait estimations to better understand plant responses to stress at scale, whether it's at the individual plant, at the individual stand, or even larger at the regional scale. So if we want to integrate these multiple layers of spectral information using phenotyping and trait estimations, we can start to feed these into different decision tree algorithm approaches to get a better idea of whether or not we can classify plant stress using spectral data by itself, meaning we don't have to go into a stand and understand and make those measurements. So here's our cartoon of a UAV that is making spectral measurements. And if we use kind of anomalous data detection approaches, we can start to say, do spectral data separate out from two different classes, if we know them, or is it different from what we would expect to be a standard response in spectral space? And then if we can estimate those functional traits, we can start to say, can we more specifically classify individual stress events, right? Not just say something is different or something is, it's less green. We can say specifically it is nutrient deficient. Specifically, it has a pathogen. Specifically, it is water stressed, right? And the reason we can do that is because plants respond in a very coordinated mechanism to all of these different stresses. There is some overlap, right? There's actually quite a bit of overlap, frustratingly. But plants respond in very characteristic ways. And if we can exploit that, then I think we can move in this direction. So I'm going to show you two different relevancy scenarios or use case scenarios for this. The first one is aerial detection of chestnut blight. We had a mixed species planting at one of the land properties here at Purdue. It was black cherry, red oak, and chestnut. And we started collecting both proximal and UAV measurements really at a very opportunistic time, where we saw the introduction of chestnut blight come into these stands, and you can see the number of trees in each class change from very low classes to very high classes in a 3-year period, right? A lot of this work was done by Sylvia, who's over there. I don't think Baroque is now with NASA, and Ali is with Bayer. So what we did is we went in and we extracted individual tree points using LiDAR, and we then captured full range spectral data using UAV in collaboration with Dr. Melba Crawford. And this is, we captured it at 3 different time points, June, August, and September, to try and capture some seasonality in these responses. We then ran it through a very basic machine learning algorithm, and we got pretty decent classification results. I'm showing you guys the two-class classification results simply because there's a lot more to it, and there's only 15 minutes. But we got really good classification. It didn't matter if we reduced the number of bands. Interestingly, the wavelength importance did change seasonally, such that predictors in earlier in the season were different wavelengths than later in the season, okay? So we were able to get really good classification overall, and one of the more interesting things about this, at least I think, from this study is that we were able to map this progression through time. So after we built this model, we went back and applied the model to all of those data, and you can see, we saw a really dramatic change in terms of score in chestnut blight severity. But if we go back and look at this, we can see that we had the yellow is a score of 0. The darker the red, the means the more severe. And you can start to see the change as it goes through time. So we were actually able to kind of map the epidemiology of the disease progression as it moved through the stands. So if we start to think about how can we identify plant stress in terms of ones and zeros or some kind of integral component, and we're talking about can we identify something that's different from a control, spectral data have the ability to do that, and they can do that as it moves through time. The next idea, if we go back to that tree, is that we need functional traits, right? It's a little harder to do right now in a stand. So for this particular case, we focused on controlled environment, potted trees, and we exposed them to a number of different environmental conditions, differences in drought, salinity, pathogen exposure, and nutrient stress. We collected a number of leaf trait data, functional gas exchange, water parameters, biochemical data. You can see all of them on the right. I think it came out to over 40 or 50 models. It was a lot. That we developed using spectral data and with the paired spectral data that we had. And we're not going to look at the model outcomes in terms of the actual model performance. What we're going to look at is the model outcomes in terms of how they predicted. And the most important thing about this particular slide is if you look at the top panel, that is all of the observed traits. So that's what we actually measured. And I cherry-picked 3 that worked really well. Photosynthesis, specific leaf area, and nitrogen. And then if you look on the bottom, those are the estimated traits. Those are what spectral data gave us. And there's no difference between the two. And what that suggests is that spectral data can be used as a surrogate for any type of reference data. The other benefit of spectral data is that one measurement can give you all of those traits that we have, right? So all of those 50 traits that would take years to measure from a reference standpoint, we can estimate with one spectral measurement. So how does this work if we start to integrate both of these? Again, controlled environment, limited extrapolation into the real world where there's more noise. But if we look at this, we can see that for our anomalous data detection, we got pretty good results. We're at about 85% where we can say something is different from a control. So if we have all of our control plants and all of our stress plants, and we put them into one confusion matrix, we can see that they classify fairly well. The interesting thing is if we move to just using the functional traits opposed to the spectral data, we actually got really good classification, meaning that the functional trait data was able to tell us whether or not something was drought stress, something had a pathogen. This was all done with black walnut as the use case. Nutrient deficiency and salinity. So it was able to do a very good job in terms of classifying individual stress events. And if you look, this is not my favorite rendering of this image, but if you look at how these fall out in terms of all of the functional traits that we have, you can see things like salinity and nutrient stress, excuse me, are positively related with osmotic potential, but not photosynthesis and chlorophyll fluorescence, other parameters that you would imagine would be related with those. You can see things like drought is related with water potential, and if you go on the other way, you can see that there's phenolic acids and other larger phenolic compounds that typically function as antioxidants. So a lot of what we're getting from this suggests that the functional traits can actually lead us into a better classification system than just the spectral data alone. So, in closing, reflectance and imaging spectroscopy, they have a lot of potential, really, to rapidly measure physiochemical measurements or aspects of different plants and different ecosystems that are otherwise laborious, time-intensive to obtain, right? The measurements can be made in living plants. You don't have to destructively harvest these plants to get an actual estimate. We can increase data volume. The amount of time that it takes us to move through and collect quite a bit of those data is a lot less than it takes to actually collect and then process and analyze those data. We can link it to genetic information. We can map these traits to understand ecosystem processes. So there's a high ceiling for integrating this imaging form into understanding forest health. And with that, I'll thank everyone and my lab.
Forgot to say we're going to follow the same format as the first plenary and keep the questions until the end. Okay, so we're going to transition from forest health to forest resilience. And I'm happy to welcome David Coombs from the University of Cambridge, who will talk to us about geospatial foundation models to transform forest resilience. Thank you.
Hello, it's a pleasure to be here to introduce Tessera, which is a geospatial foundation model which has been produced at the University of Cambridge, and we very much hope will transform the way we monitor forests in a rapidly changing world. And so Earth observation has advanced incredibly rapidly over recent decades. We now have multimodal satellites in space, satellites measuring light reflectance, optical ones, radar, LiDAR. We've also got much higher spatial resolution than we have had from space, going from tens or hundreds of meters for the pixels, all the way down to commercial satellites, which are meter resolution now. And over time, we've also got much higher temporal resolution with commercial satellites going over every single day, but satellites we're using every 8 days. So this incredible advance in the technology. What we're seeing recently is advances in the applications of big compute and AI to process these data, and that's really quite new. So one thing we want to do with remote sensing is track changes over time, and some of the things which we want to track is phenology, so when things leaf up and leaf down, senesce, and so that's what these trees, this individual tree in Panama is doing over the course of the year. And in terms of disturbance, like a fire event, we want to track over the longer term when that fire event occurred and how the system recovers afterwards. So often we want to capture information within a single year when we're doing our modeling. And so that's what we're doing there, tracking something over time. But unfortunately, we have this problem, particularly in the tropics, where there's several days or months, almost the entire year, which is cloudy, and then we only have a small window of remote sensing data, and most of it is corrupted by cloud dust or other atmospheric problems. And a solution to that is to composite the data, so to take several images and just throw them all together into a beautiful-looking European map like that one. But what we're doing there is losing the really important information we really want to keep, which is the time series. So this is where the foundation model comes along. And what it's doing is learning that annual time series in a very data-efficient way. And this model is being produced by some cleverer than me computer scientists in Cambridge. I'm on that list, but I'm not the one who's done the AI foundation model. Frank Feng, the first author, and Keshav Srinivasan at the end there, I would say the two people who have contributed most towards that. But what this this model is doing is taking data from two satellites, Sentinel-1 and Sentinel-2, produced by the European Space Agency, so optical and radar, and it's putting that data for a single year, all the data it's getting through a foundation model. And what that's doing, in essence, is compressing that information into a new embedding representation, so a new AI format. So all that data is turning into a single vector of 128 dimensions. And the very nice thing about having a single vector like that is that you can use this embedding as data and apply quite straightforward machine learning methods to it to come up with predictions. And so this can, in theory, be used for all sorts of what's called downstream tasks, maybe forest height, disease tracking, disturbance tracking, species identification. It's ambivalent to all that because what it's done is compress the data without knowing what the downstream task is going to be. I'm not going to explain this one in detail, you'll be pleased to hear, but this is in essence how the Tessera Geospatial Foundation model works. You can see on the left you've got a corrupted time series of data from an optical satellite, and you can see the missing cloudy days in that time series. And what it's doing is sampling from that time series to form two distorted images. And then it condenses them using a deep net to give these embeddings. And the clever thing is it then says, oh, well, I think those two distorted images are going to be, should be the same. The representation should be the same. And by looking at whether those two representations are the same, it fiddles around in the neural network until it comes up with the best fit to that data. And so the representation actually takes into account those cloudy days. That's been sort of corrected for, if you like, in the representation, which is a very clever technique. So now what we have, that's been trained on almost a billion points around the world. We have an embedding, one for every 10 metapixel across the entire planet per year for the last 7 years. And this is all completely open access and open code through the University of Cambridge. And this is just what embeddings look like in sort of false color to give you different parts of the earth. They're very pretty, aren't they? But are they meaningful or useful? That's the next question, isn't it? So here's 3 case studies. The first one is a bit of wildfire work by Jovna Nezovic and a PhD student with me and one of the computer scientists. And she's been looking at fire, which is obviously a major threat to forest resilience in certain parts of the world. And what people are interested in with fire is mapping where they burned, when they burned, how severe, and is the system recovering after? That's the sort of question which people are interested in. And the traditional technique for processing satellite time series is really quite painful and tedious because it requires looking at multiple time steps in the year. So you can see we're going from time -4, it's green, it's not burnt, it's burnt. Oh no, there's some clouds. Oh no, there's some more clouds. And then if we go to the next one along in that sequence, you can see that it's burnt at that stage. And then there's some more clouds. And then we see it's burnt, and it's burnt at the last two, but it hasn't been any new fires. So the traditional method would rely on sort of looking at different pairs of images to see what's happened, and that's what's being interpreted along the bottom. So it's a lot of work to interpret. It can be done well, but it's a lot of work to do that. So Tessera simplifies this by taking that temporal information and encoding it in the embeddings, so disturbance can be detected directly from the embedding. Does it work? So this is an ordination. It's called UMAP. It's a particular type of ordination. Look at the one on the right, and what we've got here is sites which have burned and unburned across America. And the fact that one is red and one's blue, the different spaces, show that the embeddings are really clearly picking up these fire events. What you see on the left is if you go back to a previous year before the fire happened, you wouldn't expect to see any separation of those points. And that's indeed, they're all muddled up. And so that's showing that we're going from from not detecting fire when there wasn't a fire to very clear detection of fire. And when Jovina took these existing fire scar maps from across the US, where people have painstakingly drawn around aerial photographs to come up where the map occurred. And she's done these sort of simple analyses of these embeddings. One is just pixel-based, so there's individual 10 meters using random forest, very straightforward machine learning approach, and one is a bit more complicated, looking at the local neighborhoods with a neural network. And when you do that, this is just one example of a ground truth data on the left, somebody painstakingly drawing it out. The pixel approach doesn't quite tally with that, and what we see is quite a lot of little bits of forest left in the burn scar, which the experts haven't picked up on. But when you look at the map, you can see that there are little bits of forest left which were left over, little refugia in the site. And that's really important for recovery of these systems, that there are little patches of forest left where the fire happened. The spatial model actually does a much better job at predicting the ground truth data, but it sort of smears out all that local detail, which is probably very important from an ecological perspective. Surprisingly and amazingly, this training on North America, we transfer it over to Europe, and it does a really good job. There's a whole lot of fire scars in Europe at predicting where those fire scars as well. So there seems to be, at least a fire, excellent transferability around the world. Second case study, this is Alan Chan and James Ball, and it's working in beautiful Scotland, where this project, called Cairngorms Connect, is taking down deer numbers across the landscape. These are lovely red deer, but there's far too many of them in Scotland, I'm afraid, because there's no predators and people feed them. But in certain parts of Scotland, the numbers are being taken right down to bring back native forests through regenerative processes. And this is what it looks like if you take the deer numbers down. You can see the pine trees are spreading, and this purple flower is heather, a shrub which is sort of a bit of a nuisance because it blocks forest regeneration if it's too dense. Here's Alan in rain and in sunshine doing some very simple vegetation plots, 308 vegetation plots, and measuring the cover in this landscape, including the forests themselves. And this literally took 3 days once he got all the data put together to fit a foundation model. And this is a pixel level 10-meter resolution map of heather cover. The accuracy was about 0.93, I think, so really, really accurate for the entire national park, Cairngorms National Park. And you can see on the right that the heather cover is gradually increasing over time, and that's because the deer have been taken out of this landscape. That's just a second example. We've done with some beautiful forestry data sets from the Italian Alps, mapping tree species there. We found that a slightly more complicated downstream methodology was needed there, where we had a little neural network on there to make the predictions. But so it wasn't just something simple like random forest, but nonetheless, a very quick process and very good at mapping species across those landscapes. Third and final example, forest regeneration, also Alan. And so we know, don't we, Juha, that you can get incredibly good maps of trees using airborne LiDAR. This is a high point density LiDAR point cloud, and these are tiny trees, sort of a few meters high, and this is our estimate of LiDAR height versus field measured height for those trees. So we can do it well with LiDAR. We can map these regenerating trees across the landscape. And the question was, can we use our foundation model? Don't bother with this LiDAR stuff. Go straight to a foundation model to come up with a prediction. Who thinks the LiDAR people is going to be out of a job with my next slide? Not really, not quite yet, but so this is our first cut. We haven't really fine-tuned the model of heights of these small trees measured by the foundation model versus LiDAR as our ground truth. And you can see there's a correlation there, and I suspect we can improve upon it. And the interesting thing is this might be good enough for the payment schemes which the government makes to get natural regeneration across these landscapes. So we might not need anything more than that, more expensive than that. So this is still work in progress. Okay, so the Tessera takeaways. This is open model, pre-computed embeddings under Creative Commons license, so you can play with it as you like, and we really hope people will play with it. It performs well for many downstream tasks. This little figure on the right shows many more downstream tasks than I've been able to present today. It's a pixel level analysis and can be done with well-known machine learning techniques. Often we're finding the accuracy is improved by adding a small neural networks onto the end, which is a bit of a shame. Usually outperforms classical analysis approaches much, much quicker than because it's self-supervised learning. So all the hard work is done in advance, like a large language model. And what we're also finding is it needs many fewer ground truth data than traditional approaches, typically sort of 30 times fewer. So that's the end, and I'm not going to answer any questions, but I would like, we're at the exploratory stage of this. We would really like people to try this approach out. As I say, it's open access. There's some things we think it won't do very well, like individual tree mapping, but there's all sorts of things where you can just try it and see whether it works, and we're really happy to help facilitate that. So thank you.
All right, thanks, David. All right, so we're going to continue broadening the discussion, or we're going to move to examine how digital forestry supports ecosystem services. I'm pleased to welcome Dr. Guy Sun from the U.S. Forest Service.
Yeah, thank you for the invitation. You know, I'm not a remote sensing or FIA person, you know, or remote or machine learning, but I'm a hydrologist. But I have the managing a program called the Eastern Forest Environmental Threat Center. So we do a lot of forest, threat kind of work. I have learned a lot this morning or today. All resonate very well of the new technology. Let's see how to move. Okay, just a little introduction about the Environmental Threat Center. Within the Forest Service, we have two Environmental Threat Center. One is the west, one is the east. So for the Eastern Threat Center, you can see from the map, basically it's east, of the Mississippi River. We do have different mission for the two centers. For the west, you can see David mentioned about all the fires, a big threat. The east, we have, invasive species, urbanization, but we have less fire. So a little bit different, but we have a lot of insect disease problem, both the east and west. But I'll just show a few applications of the digital forestry. And also, I want to show a few slides about what I do about how do you link digital forest to evaluate water resources. I have seen some poster today or upstairs. Digital forest has a lot of application in water as well, not just carbon, right? There are also other forests and providing. They are well important for water resources as well. I'll just show a few applications on that. Also, just some thought for the future research. Again, here's the mission of the Threat Center. So we established almost 20 years ago. By law, we have to monitor the national forest health. So that's why we established those two centers. One of the mission is developing a monitoring system. So I'm going to show you one of the examples. How do we monitoring the forest health at the national scale? So here's one of the example on the left is we call the FOR1 a few years ago. Bill Hargrove, developed those working with NASA. Using MODIS since 2000, right, to have this national scale, just using NEVI anomaly to monitoring what's going on the ground if there's a change of NDVI. So that's the basic principle. And later on, he moved to Sentinel-3. But that's a kind of older technology. So we also moving to a higher resolution at this point. We call it high form. Steve Norman, our scientist, is working on that. Have a lot of applications, as you can see on the right. One of the spongy moss, also some of the ice storm damage, they can be detected well with those technology. Also a bunch of other applications. For example, we use Google Earth Engine to monitor of forest change for best management practice. Because in the field survey to look at if they follow the rule of best management practice, it will be very costly. With remote sensing monitoring, they'll be more effective. Again, other application for forest inventory. This paper by Dr. Kevin Powder, just recently to look at the invasives across the nation, to look at where those invasive most severe, using the over I think the 80,000 FIA plot. I think tomorrow, Dr. Lisa he is going to talk about more in tomorrow's discussion about how Forest Service monitoring the forest inventory data, how that be applied. I think that will be our future, right? We have on-the-ground data, also have remote sensing, AI, but all those AI need validation. I think that will be a good data set that the Forest Service, we are so proud of our effort. So I saw some very good technology, but they all need validation. And so those are the kind of project that the FTech Center we are using, both FIA remote sensing data to monitoring our forest health. So again, here I want to just go a little deeper to what we're doing. One of the projects called the Forest to Facet. So basically, how do we link forest land to our drinking water? If you survey all the public, most people do not know where our drinking water comes from. You turn on the faucet, where does the water come from? Actually, most of the water comes from forest land. So with all the modeling, all the research over almost a century of forest hydrology research in the States, we have modeling to show 50% of surface water actually from forest land. If you think about 30%, they were forest land, but 50% they were provide 50% of the surface water. So probably easy to understand because forests, they were on high elevation. They are located in high ground. They have more precipitation. So they are important for surface water. So that's the project. We want to map out which watershed providing the water so we can do proper management for those watershed. So just go very quickly about this project. I put the two slides there. One is the water yield, basically how much water from each pixel, or this I think is 1 kilometer or watershed. They were very similar. If you look at the map, they were similar to forest distribution. Because forest growth needs water, and then they also provide more water. But they except some area because they were deforested, like Mississippi valley, right? They used to be forest, but they are removed by agriculture. So those on the right is basically the water withdrawal point and also the population supported by those by the public water supply. So our project basically to link those forest distribution to those water supply. Forest Service has a long history, right, back to the Organic Act. That's how the national forest was developed. Not just for timber, but also provide water, the health of a river. So, we say healthy forest equal to clean water. So protecting forest, healthy forest, they all relate to water. And again, those the numbers that we came up. Only 30% of the forest land provide half the water supply to the U.S. Water supply. Over 130 million people, they were benefited from forest land because of their drinking water. They were drained from forest land. So that's kind of the background. So in terms of forest facet project or tool, they all developed, you can access the tool through the internet. It has several functions. For example, you can provide what's the importance of each watershed. Also, what's the ability for each watershed to provide clean water. Also, we also mapped out what's the threat from environmental threat to those watershed. From insect disease, fire. A fire, they were vulnerable to fire, or land use, or also there are other climate, extreme climate, how they affect those over 80,000 watershed. So with those maps, we can provide land managers tool so they can manage those for the future. So this is just a map to show the importance of the watershed to supply water. So basically 2 factors. One is how much water they can produce. As you can see, the mountains, the Appalachian Mountains, or also from the west, in Oregon, those areas, they have higher precipitation. But another factor is how much water provided downstream of the population. Also, those 2 factors affect the importance of the watershed for water supply. So this map is showing the ability to produce clean water. 2 factors affecting this, both quantity and also quality of the watershed. If your watershed with more forest, then you provide more clean water, because the forest land, they generally have higher water quality. Also quantity. You have clean water, but you don't have a lot of water to begin with. So those 2 factors, they affect the ability to provide clean water. So you can see, even those very simple concepts, there are a lot of layers involved that. For example, riparian zone, you need high resolution to do that, and also land use, land cover types. Also, as mentioned, there are a lot of needs to look at the threat to water, both factors, right? Wildland fire, insect disease, land use, and the climate. So basically, we use both in the ability of water and the importance multiply the risk to get that index. So this map is for the threat of fire to water, about the water risk. there are other layers. For example, this is land use. We use EPA's Environmental Protection Agency, and this is projection for future land use. You can see the eastern U.S. They are expecting more land use change because of a population increase. So we project to the 2090 to give just a warning. The ability of producing water, going to change, the rest of the 21st century. Also, we are in the process to improve this tool, because this tool is, we developed 5 years ago. And we are adding more complexity to this. For example, we are using the real water quality instead of the surrogate of land use to improve that from the USGS data. There's lots of change, since the last 5 years of the digital technology. For example, groundwater mapping. 5 years ago, we do not have that, but today they can map with machine learning to 30-meter resolution of groundwater table depth. So that's a big change. Also, we are updating of the interbasin transfer. Was not in the original forest facet, so that we can provide the value for certain watershed. They can benefit down across the watershed, called interbasin transfer. There are also this fire. We put a lot of effort to evaluate fire impact on water quality. We are using Google Earth Engine to look at the fire kind of modeling to look at the fire impact on soil erosion, so we can see where those are most vulnerable to soil erosion. So for future research, I think a few ideas. Here is a higher resolution. I think we recognize that land managers require a better resolution. Like our forest we call the forewarn for the national scale monitoring of forest health. Those national maps, they are useful to look at where they were most vulnerable, but the land manager needs their local information. So we need to look at a more higher resolution to do that. And so we need the monitoring everywhere all the time. I like the Institute of Digital Forestry wire. Every tree. So we need monitoring everywhere all the time. So better integration. As you can see, many speakers talk about this forest stress. Forest stressors, they are not act individually, they act all together. So we need to integrate all the stressors, biology or abiotic of stressors. We need more intelligent, cost-effective. That's how I think the AI technology to link those. And so you all know this. So here's one example. In terms of, I'm involved into this project. Basically, we want to map out, have a higher quantification of water use by trees at a large scale. This is the kind of a first step, first project. We link FIA to hydrology, to evapotranspiration, to transpiration of trees. We have a postdoc is working on this. So basically, we have measured tree worldwide, across the US. We put sensor on trees, but how do we scale up to plot scale, to pixel scale, also to regional? Because as mentioned, forests affect a lot of water resources. Forests use a lot of water in order to get the carbon, provide all the ecosystem services. So they are competing, actually, water resources. We need to better quantify different species, conifer versus deciduous. They use very different water. And we have watershed monitoring across the US. Forest Service has this 100 years of history to monitor watershed. So we want to understand how managing forests to affect water supply. So we need to do that, and so those are the kind of the step using machine learning, link for FIA plot data, the DBH versus the sapwood area to do that. And there are other validation technique. Adiflex tower, we use that for our validation. So here is just is still working, but this kind of this flapping every day. We can map the transpiration of water use per day, from a few millimeter to 8 millimeter per day for two species. Here is for tulip, poplar, and also pine per pixel. So that's kind of a direction we are doing to get a more species level of water use. So also we are looking at AI technology to how do we monitoring and assess forest stress. So this kind of this is a paper from Dr. Qingfeng Guo. He's doing his career on forest invasive. He wrote this paper of AI technology, how that apply. Overview, as you all probably familiar with this. We look at biology, biotic, and abiotic disturbance, also human impact, to have a comprehensive evaluation of the treat of what we have been monitoring. So those AI tools, different technologies. Today I have learned a lot about those technology, how they use. But the goal is to forest health monitoring of a short-term and long-term monitoring. Those tools will be very useful. I think that's all I have. I'd like to acknowledge all my colleagues and our postdocs for this paper. Thank you.
Okay, so I'd like to invite David and John to both come back up, and we'll steal a little bit of time from the break to have some questions for all three speakers. Any questions?
For David, do you have any guess at how far back you could pick up a signal of a past fire, given your embeddings?
So you pick them up within any year, and Jovan has actually been working on interpreting the embeddings, which is one of the problems with these AI approaches. What does it actually mean? And you can pick up within a few weeks when the fire happened. You can't get it down to the day. And this approach only goes back to when the European Space Agency launched Sentinel-1 and Sentinel-2. So we're using mid-2017 to the current day. People are using similar approaches for Landsat, but we haven't done that.
Hi, again for Dr. Coombs. Have you done any analysis, comparison with Alpha Earth from Google?
Oh dear. So our product is very similar in many ways to Alpha Earth, except we actually we actually outperform them on various tasks, and I think the reason for that is actually ours is I say ours, but most of the work was done by the computer scientists here. Ours is a much simpler product, and it just uses the 2 types of satellite imagery. It's not throwing in other types of data into the mix in an obscure way. And both products have some tiling problems at the moment, but we're version 1.1 is being run at the moment, which will get, and there won't be sort of nasty tiles, which you often see on the Alpha Earth products. We're completely open source and open data. We would love to have the money and resources of Google to have a Google Earth engine platform, and I think it's what academics should be aiming at collectively, to not be relying on these massive corporations for their compute, because we can do it ourselves, but that's an issue for another day, perhaps.
Thank you.
All right, last call for questions. All right, if not, you are also welcome. Oh, we do have one more. Yes, sorry, go ahead.
Yes, for David, how do you deal with the uncertainty on the, like the embeddings for the model?
The uncertainty generated, for example, by the path of Sentinel-2 not being that sort of uncertainty.
Yeah, exactly, from the sensors.
It's a very good question, which I can't answer in one sentence. But I would say actually it's very early days, and we're a small community, and actually error propagation is clearly an issue which we all need to think about with these foundation models. So there's the sort of sensor problems, but also aligning field data with all its geospatial inaccuracies alongside embedding. So I haven't got a good answer for that. I'd love to chat with you about what we should be doing.
Sure thing, thanks.
Okay, so we are at a break. Our speakers will presumably be around, and so if anybody has other questions, you're welcome to track them down. I want to thank all of our speakers today for an interesting and invigorating series of talks. We, from 5 to 6, are on a break, so you're welcome to continue the conversations from earlier or go for a walk outside. Dinner won't be ready until 6 o'clock, but don't be late for dinner. I do want to mention also that there is a private event going on across the hall in the back, and they don't want us to mix with them. So stay on this side of the velvet ropes. All right, we'll see you all again at 6 o'clock. Thank you.